Hi there matriculants and welcome back to NTE. Right, so in response to the Minister of Basic Education's announcement of your rewrite, I decided let us get our heads back into the game and start to really recall our theory when it comes to Maths Paper 2. Right, so I've decided to use the Northwest Province, right, prelim paper. So we're going to go through this paper in order for us to prepare for our rewrite. Okay, I hope this helps and absolute best of luck for everyone who's going to be sitting down for that paper. With that said, let's get started. Right, the easiest place to start with your Maths paper 2 is always your proof. Right, so in this paper, this is question number 9. It says in the diagram below, chords AB, BC, and AC are drawn in the circle with a center O. DCE is the tangent, right, to the circle at C. We now need to prove, right, we all know this theorem. Prove the theorem that states that angle ACD is equals to angle ABC, right? Which theorem is this one? That's the tan-chord theorem, right? So I've just redrawn the structure over here. What we are required to prove is that the angle ACD, right, so this angle right over here, right, we want to prove that that angle is equal to the angle ABC, right, so this angle over here. Right, so if you can remember from theory, right, you should remember that in order for you to successfully prove the tan-chord theorem, right, you need to find those two angles that are equal to 90 degrees, right? And just remember that one of them is always that angle in a semicircle, right? And then the other one is always the angle, the 90 degrees that's formed by the radius or the diameter being perpendicular to the tangent, right? So before we begin this, we need our construction, right? And for this specific theorem, our construction is always that diameter, right? So we're going to write it down, but I'm just going to draw it in for now, right? The first thing you're going to say is that you are going to construct a diameter in this circle. Right, and then remember, once we've drawn in our diameter, right, we then need to join this diameter to one of these vertices, right, either the vertex A or the vertex B. We always join it to the vertex away from the angle that we're trying to prove. So we're trying to prove this angle B over here. So we need to then join away, which is going to be joining to A. Okay, so we just need to put a point over there, right? And then after that, we need to note down our constructions. Right, so now that we've noted down what did we do for our construction, just by the way, I decided to call this point over here the point F, okay? So in order to continue with our construction, we now need to locate those two 90-degree angles that we were speaking about. We know that the first one, right, is going to be located right over here at the point of tangency, right? And the connection between that point of tangency and the diameter, we know that that is always a 90-degree angle. Okay, let's just try that again. We know that that whole angle is 90 degrees, right? And we're noting the fact that that 90 degrees is actually containing this angle that we have to work with, okay? Which means that we are actually going to have to work with this smaller little angle, angle ACF, okay? Right, so we found one of our 90-degree angles. Where is the other one? Well, the other one is now created over here. Now that we have the diameter, right, subtending an angle at the circumference, we know that that angle is called an angle in a semicircle. So that is our second 90-degree angle. Right, so we've now located our two 90-degree angles. Let's work with them. Okay, so we're going to first state the fact that angle FCD, right, that full angle FCD is equals to 90 degrees, right, and that's because the diameter of a circle or the radius of a circle is always perpendicular to the tangent. Okay, remember that we were told, if we go back here, that DCE is the tangent. Okay, So DCE, we were told that that is the tangent. Cool. Next thing we need to state is the fact that now angle FAC, right, FAC is also equals to 90 degrees. The reason for this is because this is an angle in a semicircle. Right, so because we're using this complex way of talking about the angles, this proof is going to look a little bit difficult, but it really isn't. Right, I don't want to add too much information to this diagram because it wasn't really labeled. But if you want to label things like angle C1, angle C2, angle C3, you can do that if it makes it a little bit easier for you to follow. Okay, so what I'm going to do now is I am going to pull out these two angles, right, which are contained within angle FCD, right. So I'm going to say, but angle FCD, right, is equals to angle ACD, right, plus angle ACF. Okay. Right, so then therefore, in fact, what we're saying is that the angle ACD, right, that is that angle between the tangent and the chord, if you can remember, right, plus that small little angle inside of this triangle, this right angle triangle AFC, right, that is what is actually equals to 90 degrees. Okay, all right, and then I'm going to add to this that and, right, in that right angle triangle, right, angle AFC, right, angle AFC plus angle ACF, right, so this angle up here plus the small little angle over there, right, sum of interior angles of the triangle, those must equal 90 degrees as well. Okay, and my reason here is exactly that, sum of interior angles of triangle. Which triangle is this? AFC. Okay, so what do we have right now? We've got two equations that are equal to 90 degrees, right? So if you call this equation 1 and you call this equation 2, right, we know that 90 degrees is equal to 90 degrees. So therefore, equation 1 has to equal equation number 2, right? This means that angle ACD plus angle ACF is equals to angle angle AFC plus angle ACF. Right, so now you can see that you have the angle ACF on both sides of your equal sign. So those ones will cancel out. Okay, and now what we have is that angle ACD, right, is equals to angle AFC. Okay, so now what we've proven is that this angle between the tangent and the chord, ACD, right, so I'm going to put a line through it, just that angle over there. We've now proven that to be equal to this angle up here. That is very good news because you can see that when you look at that angle AFC, right, that is basically an angle in the same segment with the angle ABC, right? So we can state that and we can say, but again, right, angle AFC is equals to angle ABC, right? And the reason for this is angles in the same segment, right? Angles in the same segment. Right, and you can also add over here that these two are subtended by, right, let's just see what they're subtended by. They're subtended by the chord AC, right, so subtended by AC. Okay, so now you can do a substitution for the angle AFC, right, so now you have that therefore angle ACD, is equals to angle ABC, right? And this is exactly what we were required to prove, right? That angle between the tangent and the chord is equals to the angle in the alternate segment. Okay, and you are done. Right, so now that we're done with our proof, you can now go back and actually attempt your statistics, right? So statistics, question number 1 and question number 2. Here we go. Question number 1 says, during the 2019 Rugby World Cup, the South African Springbok players played 7 matches, right? The score obtained in each match by the Springbok players is given below. Okay, so we've got a score of K, 19, 2K, 30, 32, 49, 57, and 66. Okay, they say that the average score obtained by the Springbok players during the 7 matches that they played, right, was 37.43. Okay, first question wants us to show that K is equals to 13, right? Okay, so for this one, we can obviously tell that, well, since K is part of our data set, obviously then we need to use this information about the average, okay, in order to calculate or to show that the value of K is equals to 13, okay? So we know that the average, okay, X bar would have been calculated by taking all of these scores okay, and dividing them by the number of data sets that we have, and we know that this is basically the scores for 7 matches, right? We're given that the average is 37.43. Okay, so now you can see that this is the equation that we need to solve. We can clean up the numerator, right, by actually simplifying all of these like terms, right? The first thing that we're going to have is this K plus 2K is going to be a 3K, and then we just need to add all of these other values together, and then we are going to be able to solve for K. Okay, so if you solve this on your calculator, you get that K is equals to 13.00333333 recurring, right? And remember that the instruction is always to round off to 2 decimal places, so this basically becomes 13.00, which then shows that K, in my opinion, is approximately equals to 13, but nevertheless, we've now shown that K is equals to 13. Question 1.2 says calculate the standard deviation of the data. Well, now what we know is that our data is actually the data set 13 for K, right? And then we're going to have 19, and then we have 2 times K, right, which is 26, and then we're going to have 32, 49, 57, and 66, right? So this is our data set. We now need to then basically calculate the standard deviation, and for that we just need to plug all of this into our calculator. So let's grab our calculators. Right, so the most important thing to do, right, when you actually start these questions is to clear the memory of your calculator. Okay, so before you do anything, remember to clear the memory of your calculator, and you always do that by going Shift 9, right, and then press 3 to clear all and equals to confirm. Okay, AC, right. Okay, so now we have to plug all of these values into the stats mode. So we're going to go mode 2, and we're going to choose option number 1 right now because we're only looking at univariable data, right? So we only have one single data set. Okay, we have the first set as 13, and then 19, 26, 32, 49, 57, and 66. Okay, we press AC, right, and that basically makes it seem like we've lost everything, but we all understand that that has now gone into the memory of the calculator. Okay, we're now going to press Shift 1, right, which is basically Shift Stats, in order to obtain more options, right, for the statistics. Okay, what are we looking for? We're looking for standard deviation, right, so that is a variance, right? So look on your calculator where you have variance. For my calculator, that is option number 5, so I click on that. Okay, you can see over here we've got n, which is the number of data sets, we've got 2, which is your mean, and we've got 3, which in this case is my standard deviation. Okay, so I'm going to press 3 equal, right, and we all know that we have to write this to 2 decimal places, so I'm going to immediately write this as 18.63. Okay, so 18.63 is the standard deviation. Okay, question 1.3. Right, let's just remove the calculator for now. Let's see. It says the 2 highest scores lie outside P standard deviation of the mean. Right, calculate the maximum value of P. Okay, so this is talking about that whole thing where we say sometimes that we're looking at 1 standard deviation above or below the mean, right, or 2 standard deviations above or below the mean. Okay, over here we don't know exactly whether is it 1, 2, 3, or 4 standard deviations, right? We're just saying that we're looking at P standard deviations, right, some unknown value. Okay, and we're specifically wanting to look at the maximum one. Okay, so if we had to write this out, okay, we would usually have this in like a coordinate form, and then we would say we are looking at let's say 1 standard deviation below the mean, so you would have the mean minus a standard deviation, and then you would have 1 standard deviation above the mean. Okay, so the mean plus a standard deviation, right? That's what we usually write, but right now we're looking at just the maximum, so we just want to concentrate on this part of our coordinates. Okay, so then we want to just say that the standard deviation plus some P value, okay, that we don't know, right, that has to basically equal, in this case it has to equal 57. Okay, that is basically coming from here. It says the 2 highest scores, right, which is 57 and 66. We're told that those 2 scores lie outside, right, of this interval. Okay, so if we want to look at the maximum value of P, it makes sense to then set this equals to the most immediate value outside of the interval, right, which in our case is 57. Okay, so we now have the value of the mean, right? It was given to us over there as 37.43, and we just calculated the standard deviation above. Okay, so we can do those substitutions. So 37.43 for the mean plus this unknown P times the 18.63. This must equal 57. Okay, so then we can solve this for P, right? We're going to have P times 18.63 is equals to 57 minus 37.43, that is 19.57, and then therefore P will equal, divide that by 18.63, right, and we get that P to 2 decimal places is 1.05. Right, so moving on, question 1.4, says sappose each score is increased by adding a value y, okay, to each score. 1.4.1 says write down the interquartile range for the new data set. Okay, I don't know exactly why they say write down, because that is not so obvious, but let's just think about it quickly. Right, so this is the old data set, right? The new data set is going to have all of these values increased by some value y. Right, remember that we have 7 data sets over here, so 7 is an odd number, so it's actually quite easy for us to locate our Q1, Q2, and Q3, right? You can do this even with your fingers on screen, right? Right, so covering each of the points, right, from each end and moving to the middle, right, will tell you that 32 plus y is basically our median, right? This is Q2, right? Now we have the lower half of the data set. If we divide this as well into equal halves, right? So basically moving inwards, you will have 19 plus y as Q1, and then 57 plus y as our Q3. Right, so we are looking for the interquartile range. We know that that is equal to Q3 minus Q1. So we have 57 plus y minus 19 plus y. Okay, so we're going to have 57 plus y minus 19 minus y. The y's cancel out, leaving us with 57 minus 19, which is equals to 38. Okay. 1.4.2 says calculate the value of y, okay, if the lower quartile, right, of the new data set is 30. Okay, so this is basically sort of like an equation. We've already identified our Q1, right? So we now have basically that Q1 must equal 30, right? We have an equation for Q1 that is 19 plus y, and that must equal 30, right? So then therefore y is going to equal 30 minus 19, which is 11. Okay. All right, question number 2, right, is a whole story about two popular swimming pools, right, in a municipal area. There is the Madiba swimming pool and then the Corion swimming pool, if I am pronouncing that correctly, right? And what we have over here is a data set for 8 different days where we have basically what the temperature was and how many people actually visited the swimming pool, right? This specific data set is speaking about the Madiba swimming pool. Okay, so let us just quickly look at this data. It is a little bit tricky because it is not in chronological order, right? So if we try to rearrange it, we have that when the temperature was 18 degrees Celsius, we had 180 people, and then from 18 we need to go into 22 degrees Celsius, we have 200 people, and then we have 24 degrees Celsius, 210, 28 is 350. From 28 we need to, I missed the 26, so 26 we have 280 people, and then 28 is 330. Then we need to go to 30 degrees Celsius, which is 300 people. And I have just noticed now I've missed the 20 degrees Celsius. So let's just put it over here. So 20 degrees Celsius is 195. And then 18 was 180. Okay, so let's see. We've got 18, 20, 22, 24, 26, 28, then we need 30, and lastly 34 degrees Celsius. We had 410 people. Okay, so what do we have over here, right? We have that our temperature, right, this is our temperature in degrees Celsius, right, that is basically increasing over these 8 days, right? Okay, so now that I've arranged it in increasing order, okay, what is happening to the number of people that were visiting these the swimming pool, specifically the Madiba swimming pool? We see, okay, it's increasing, and then over here at 28 degrees Celsius we have 350, but then after that it goes down to 300. So we can sort of like think to ourselves now that because of that, okay, there isn't really going to be such a strong correlation, right, between what the temperature is and how many people actually visit the swimming pool. There's other factors that are playing into that are in play here, right, that are contributing to when do people actually decide to come to the swimming pool. Okay. If I look at the questions, for question 2.2, we just asked to calculate the value of the correlation coefficient. We're not really asked to say whether is it strong or weak or anything like that. So, okay, for this specific paper, we don't have to worry about that. But if you had to comment on whether is this going to be strong or weak, it will depend on the value, but then this one would not be very strong. You'd probably just say strong. There's a strong positive correlation we can see over here. It's not a very strong positive correlation. Okay. Right, but anyway, let's get into the questions. Question 2.1. Right. It says determine the equation, right, of the least square regression line for the data. Okay, so we know that for this we need our calculator. Right, so back in our calculator, we're now going to go back into mode, right, press 2 for stat, and now we have bivariant data, right, we've got two data sets, so we need to pick option number 2, okay. We're going to see these two columns, right, we're going to use the column X for our temperatures, right, so we're going to insert all of that, right, and then we're going to scroll back up, and then use the Y column to record the number of people that visited the swimming pool. Okay, so there we go, all done. Right, again we're going to press AC, and then we're going to go shift 1, right, and this time what we're looking for is under regression, right, so we're going to go into 7 and we're looking for these values of A and B, right. So let us just quickly note down that our least square regression line is in the form Y, sort of like Y hat actually, is equals to A, right, plus BX. Right, and we always write it in this form, specifically, right, for statistics. So here we go. Y hat is equals to, what is the A value? Okay, so to 2 decimal places, this is negative 106.95, so negative 106.95 plus, okay, now we need the B value, so we go back to shift stat and then back to 7, and then we grab the B value, is equal, but that is equals to 14.76 if we write it down to 2 decimal places, and we have your X. Okay, so there you go, there is the equation of your least square regression line, or what we call the line of best fit. Okay. Question 2.2, let's just move this. Right, it says calculate the value of the correlation coefficient. Right, remember the correlation coefficient is basically the value of R. That is going to be from the calculator. So if we pull the calculator back up and we go shift 1 again, back into regression, and this time we're going to go into option number 3, press equal, right, we see that our regression, right, is basically 0.94, right, which again just confirms the fact that yes, we have a positive strong correlation between these two data sets, but not a very strong correlation. Okay. Right, question 2.3 says the manager of the swimming pool, right, asked one of the grade 12 learners to predict how many visitors, right, he or she can expect on a day where the temperature is 32 degrees Celsius, right. This specific learner says that we can expect 365 visitors, right, and the question is, should the manager take this prediction seriously and actually prepare for 365 visitors? We need to motivate our answer. Okay, so for this, right, we know that basically what the student did is that they found the equation like we did, and then they substituted that temperature, which in our case is sort of like an X value. Yes, it is an X value, and then we calculate Y, right, the output, which is basically the number of visitors that you can expect. Okay, so 2.3, we have that Y bar is equals to minus 106.95 plus 14.76, and in place of X, we're going to substitute that 32 degrees Celsius. Okay. Right, so if you plug this into the calculator, you get that y bar is equal to 365.37. Okay. Alright, so we can actually then conclude that because this is basically talking about visitors, right, we would have to then round this off to the nearest 100, right, which is then therefore 365 visitors to be expected. Okay, so this calculation over here is basically forming part of this, or answering this part of the question, which is to motivate your answer. Okay, let's answer the other part. The other question was, should the manager take this prediction seriously? All right, we can now say yes, so therefore yes, the manager can take the prediction seriously. Right. Last question, 2.4, right, it says, over the same period, right, of 8 days, with the exact same daily maximum temperatures, right, the other swimming pool, right, that swimming pool also recorded the number of visitors for each day. Okay, the equation for the least square regression line for this specific swimming pool conjure, whatever it is, right, is given by y bar is equals to k plus 12.85x. Okay, the question is, which swimming pool had the highest number of visitors over the period of 8 days? Okay, motivate and look over here. For the first time, they're saying without any calculations your answer. Okay, all right, so let's look at this. Right, we know that normally, right, this equation of the least square regression line would be actually on a scatter plot, right? So if we think of our scatter plot, we would have our y-axis, we would have our x-axis, right? What goes on the y-axis, right? Our independent variable, right? So what is the independent variable over here? Well, the independent variable over here is the number of visitors. Okay, so the number of visitors would be here. So number of visitors. Okay, and then what is the dependent variable? Basically, think about it. The number of visitors is dependent on the daily temperature. That's the maximum daily temperature. Okay, so what we have is that for the one swimming pool, right, the Madiba swimming pool, we calculated that our y bar, right, was equals to minus 106.95 plus 14.76x, right? Then they're telling us that this other one, okay, is y bar is equals to some unknown y-intercept plus 12.85x. Okay, so I think that because they've made the y-intercept unknown, what we really have to be looking at here is the slopes. Okay, so what do we know about slope? Okay, we know that slope is basically a rate of change. Okay, so we can think of the fact that the one that has the greater slope, right, has a greater rate of change, right? So what do we mean by a rate of change over here? Well, a rate of change for us would be dy over dx, or basically the change in the number of visitors over the change in temperature, right? That is equals to the slope. Okay, so now, as we said, the one with the greater slope, right, represents a greater rate of change, right? And specifically, what is this greater rate of change? Well, it's a greater number of people, right, per change in temperature. Okay, so greater number of people basically means more visitors, right, coming to your swimming pool. Okay, so to answer this question, which swimming pool had the highest number of visitors over this period of 8 days? That would have to be the swimming pool. Oopsie, I'm not in highlight mode. Okay. Right, there we go. Right, that would basically be the swimming pool, right, the Madiba swimming pool. Right, so hopefully you're able to follow this logic, right? We're saying that the Madiba swimming pool, right, had the highest number of visitors over this period of 8 days, right? Because we noticed that people were actually visiting the Madiba swimming pool at a much faster rate compared to people visiting the Kunja swimming pool, okay? And where did we get this idea of rate? Well, basically we know that rate is talking about slope. So we just basically noted that the slope, okay, how are we going to state this? The slope of the Madiba, right, swimming pool is greater than the slope of the other swimming pool. Okay. Right, so now we've reached question 3. Which is basically our analytical geometry. Okay, so it says in the diagram below, A with point negative 20, 64, B and C are the vertices of a triangle, right? Triangle ABC. With C, a point on the x-axis, right? And we can see that right over there. Okay, we have that D is the point negative 12P and E is the point 926. And these two, right, are the midpoints, right, of the two line segments AC and BC. Okay, we also have that KC, right, where is that? Is equals to 16 units. All right, so this distance KC is equals to 16 units. Okay, all right, so let's put that in over here. That is 16 units. Right, so what else can we pull out of this given information? Quite strikingly, something that we don't usually see quite a lot. I'm not sure if we're going to use it here or not, but we don't actually get reminded of the midpoint theorem, but we can see it over here. Right, we know that when we have a line joining the midpoints, right, of two sides of a triangle, right, then what happens is that that line, right, which in this case for us is DE, right, so DE ends up being parallel to the third side of the triangle, which is AB in this case, and also that line DE, okay, is equals to half the length of that third side, right, AB. Okay, so this over here is the midpoint theorem. Okay, so we now know that DE is parallel to AB. We might use it, we might not, you never know. Okay, so let's look at the questions. Question 3.1 says the gradient of AK, right, is undefined. Well, what do we know about a gradient that's undefined? We know that the only line that has an undefined gradient is a vertical line. Okay, so basically what they're telling us is that this line AK is basically vertical. Okay, so in other words, it forms a 90-degree angle here at the where it meets, basically where it cuts or intersects the x-axis. Okay, so which means that the x value over there is exactly the x value here at A, which is an x value of minus 20. Okay, so now if we have to write down the equation of that line, well, that is basically going to be the equation x is equals to minus 20. Okay, remember that for any vertical line, the equation of a vertical line is always x equals, right? This is in contrast with the equation of a horizontal line, which is in the form y equals something. Okay. Question 3.2 says calculate the x-intercept of the line AC. Okay, so there's the line AC. The x-intercept is that point C. Okay, so calculate the x-intercept, right? So we just want to find out what is the x value here at C. Okay, so we were given, right, that the distance KC is equals to 16 units. Okay, so basically now we can basically set up the equation that the x value at the point C, right, minus the x value at that point K, which we know is an x value of minus 20, that must give us a distance of 16. Okay, we're looking for this x value at the point C, so this is then 16 plus the x value at the point K. Right, so substituting that in, this is plus negative 20. Okay, so then the x value at C is equals to, basically this is minus 20 plus 16, which is going to be minus 4. Okay, so we now know that the coordinate there is basically minus 4, 0. Okay. Moving along, question 3.3 says, calculate the length of the line segment AC. Well, that is now going to be purely the distance formula, right? So you're going to have AC is going to equal, right, the square root, okay, of the change in the x values, right? So let's start here at C and go upwards. So that's going to be minus 4 minus negative 20, and all of this squared, plus the change in the y value, so that's going to be 0 minus 64, and that has to be squared. Right, so AC is equals to, right, so if you plug all of this into the calculator, you get that the length AC is equals to 16 root 17 units. Okay. Question 3.4. It says show that the value of P is equals to 32, right? So P is located here in this coordinate of D. What do we know about D? We know that D and E are the midpoints, right? So let me just do this. Over here we have made these dark dots, right? Those 2 points are midpoints. Okay, so in order for us to look at showing this value of P, we can use half of our midpoint formula. Okay, that is a y value, so we know that that value P is equals to the average of the y values of the connecting points, right? So that's going to be the y value at A plus the y value at C, and we said the average, so we need to divide this by 2. Okay, so P is equals to 64 plus nothing, right, divided by 2, so then therefore P is equals to 32. Right, on to question 3.5. It says determine the equation of the line AB, right? So there is a line AB over there, right? So in order to find the equation of the line, we need the gradient of the line, and we've already noted that AB is parallel to DBE. E, right? So you can see that we can definitely calculate the gradient of the line DE, and because these two lines are parallel, those two gradients are going to be equal. Okay, so we are going to basically have to state all of these facts first, right? We are going to have to say that DE is parallel to AB, and our reason for this is exactly what we said, the midpoint theorem. Right? So then from that we now know that since we now have parallel lines have equal gradients, so the gradient of DE is equal to the gradient of AB. Okay? Once we have the gradient of AB, finding the equation of AB is not going to be so much of a hassle because we just need a point that lies on the line AB, and we do have that point, that is the point A. Okay, so let's find the gradient of DE, right? Our change in y values, right? If we start here at E, that is going to be 26 minus 32 divided by the change in the x value, so 9 minus negative 12. Okay, we plug all of that into the calculator, it works out to a gradient of minus 2/7. Okay, so then therefore the gradient of AB is equal to minus 2/7. Okay, so now we're going to go into the equation. Y minus the y value at A, right, is equal to the gradient of the line AB into x minus the x value at A. Okay, so we're going to have y value at A is 64 equals to negative 2/7 into x. Then we're going to have a double negative here, so this is just basically plus 20. Okay, so we have y minus 64 is equal to negative 2/7x minus negative, or basically 2/7 times 20, that is 40/7. Okay, so then therefore y is equal to negative 2/7x, and then minus 40/7, right, plus 64, that gives you positive 408 divided by 7. Okay. Right, question 3.6. We asked to calculate the size of the angle KAB. Right, so the angle KAB is this angle over here, KAB, this full angle over here. Okay, this is quite a lengthy question unless you can see a shorter way to do this, but I'm basically aiming to calculate this angle, right, using one of the trig ratios, right, in this right angle triangle AKC, and then I am planning to calculate this piece of the angle, right, where I'm putting dots, using the cosine rule, because with the cosine rule I just need the length AB, right, which I can get from this property over here, and I need the length AC, which we already calculated in 3.2, that is 16 root 17 units. Okay, and yeah, can use the cosine rule to then calculate that included angle. Okay, right, so let's just quickly go through all of these calculations quickly. Right, so basically where I started off is in this triangle AKC, right, so this right angle triangle over here, and I calculated this angle KAC, right, that angle that is shaded in black. Okay, so for that I used the trigonometric ratio of sine, and I found an angle of 14.0362, right, if I write it to 4 decimal places. Okay, so I was then done using that right angle triangle. Then I moved on to using the triangle ABC, which is obviously not a right angle triangle, so I had to then go for the cosine rule. Okay, Right, but then the cosine rule then basically demanded that I have certain lengths defined, right? So I first calculated the length, DE, right? Because I know that I can use this relationship over here to find the length AB, right? So when I calculated the length of DE, that came out to 3 square root of 53. So then you just times that by 2, and then you get that AB is equals to 6 root of 53. Okay, so now you have the length of AB. And then it was necessary for me to calculate the coordinates at B so that I can calculate the distance BC, right? So in order to get the coordinates at B, we use this midpoint, right, point E, and we basically say that the x value at that midpoint, which is 9, is equals to the x value at C plus the x value at B divided by 2. That makes the x value at B to equal 22, and then you do the same calculation for the y values to give you that the y value at B is equals to 52. Okay, from there you can then calculate that the length BC is equals to 26 root 5 units. Okay, so then moving on to this triangle ABC, so ABC, okay, you now have that the cosine rule says that that side which is opposite to that included angle that we're looking for, which in this case is the angle CAB, right, that side which is BC squared, right, is equals to the other two sides squared, so AC squared plus AB squared, right, minus 2 times the product of those two sides, so minus 2 times AC times AB times the cosine of that included angle. Okay, so I didn't have enough room to show all of the rearranging and substitutions, but basically you have the length of BC right over here, you have the length of AC from 3.2, and we have it up here as well. AC is equals to 16 root 17. Okay, and you also have the length of AB, you calculated it over there. Right, so just substitute in all of those values, and then you're able to calculate that that angle which I showed with dotted, with a filled in dot, is equals to 60.0183 if I write it to 3 decimal places. Okay, 4 decimal places, sorry. Okay, so then to answer this question, right, question 3.6, the full angle KAB, right, is then equals to the sum of these two angles KAC and CAB, which then gives us a final result of 74.05 degrees. Okay, quite a lengthy question. Right, so then going for the last question, question 3.7. Okay, they say if angle KAC, right, so KAC, right, is equals to 38.67 degrees, right, determine the area of the triangle ABC. Okay, so KAC, right, they're saying that if that angle is equals to 38.67 degrees, okay, we need to then determine the area of the triangle ABC. I don't necessarily see how this angle would be related. Oh, okay, so remember we had that the full angle KAB would equal the angle KAC plus CAB, right? And we calculated that this full angle is 74.05 degrees, okay? And now they're saying that this angle must be 67 degrees. So I'm guessing that is going to help us to calculate the angle CAB. Okay, so therefore the angle CAB has to equal 74.05 minus 38.67. So that gives you 35.38 degrees. Okay, so then over here we wouldn't have this calculated value. We would actually have 35.38 degrees. Okay, so now for the area of that triangle, right? So area of triangle ABC. Okay, we now know we're going to use the sine rule over here. We need half, right, to the including side, so that's going to be AC times AB times the sine of the included angle, which in this case is this angle CAB. Okay, so we have half of AC is right over there, 16 root 17. AB is 6 root 53. And we're taking this for the sine of 35.38 degrees. Okay. Right, so if you work all of this out in your calculator, you get that the area of this triangle ABC is approximately equals to 834.22 units squared. Okay. Right, so that brings us to the end of question number 3. Right, so now on to question number 4. Right, it has that in the diagram below, the equation of the circle which is centered at F is given as x squared plus y squared minus 6x plus 4y is equals to 87. And the equation of the circle centered at M is equals to x minus 4 all squared. Sorry, x minus 14 all squared plus y minus h all squared is equals to 25. Okay. We have the point 9 minus 10 which lies in the circle which is centered at F. Jn, what is that? Oh, okay. Jn and KL are tangents to the circle F, right, at the points J and K respectively. Okay. These two circles touch externally, right, and we know that basically, if we remind ourselves of the theory, we know that whenever two circles touch externally, then the distance between their centers, right, is just given by the sum of their radii. Okay, so we usually refer to the radius of the big circle as capital letter R and the radius of the smaller circle as small letter r. Okay, so then we know that when we take the sum of these two radii, it gives us the distance between those two centers. Okay, so let's see what the question says. Question 4.1 says write down the length of the radius of the circle with center N. Okay, so let's just note the equations over here. Right, this equation is x minus 14 all squared plus y minus h all squared is equal to 25. Right, that's the equation of this circle centered at M, and then the equation of this larger circle is given as x squared plus y squared minus 6x plus 4y is equal to 87. Okay, so question 4.1 wants us to write down the length of the radius of the circle centered at M. Well, we are given that the radius squared is equal to 25, so then the length of the radius R is just going to be 5 units. Right? That's basically just the square root of 25. 4.2 says determine the coordinates. Sorry, let me just move this down. Okay, we need to determine the coordinates of F. Right, so F I've now cancelled it over here. If you look back in the original sketch, right, F is the center, right, of this larger circle. Okay, so we know that we can get that by basically completing the square on this standard form. Okay, So the first thing we would do is that we would collect our like terms. So we'd write this as x squared, and then we'd follow it up with the minus 6x, and then we'd leave a space, and then we'd write in y squared plus 4y is equals to, we need to leave a little bit of a space there again before the equal sign, right, and we still have that 87. Okay, so what are we doing now? Well, now we're basically completing the square for our x terms and our y terms separately, right? So we're going to have half the coefficient of x, right, which in this case is minus 3, right, and that has to be squared, right? So we're going to be adding half the coefficient of x squared, okay, in that little space that we left. And just by the way, the reason why we are going straight into the method of completing the square is because the coefficient on x squared is equals to 1, right? For the same reason, because the coefficient on y squared is also equals to 1, we go directly into the process of completing the square, right? So we're going to take half the coefficient of y, right, and then square it. Okay, so half of 4 is 2, so we're going to add 2 squared, right? So now these two things that we added, we then have to add them on the other side of the equation as well. Okay, like that. Right, so now if you watched that live video that I did for the Gauteng prelim exam, you realize that in that video I noticed a little bit of a loophole when it comes to the shorthand method of factorizing from here, right? So basically when I thought about it afterwards, which is kind of the reason why I'm using this question as well, right, is because I want to point out to you that when we use that shortcut method, right, remember that we say that we just open brackets, right, and what we do is that we drop the x, we drop the sign, right, and then what happens is that if you have a negative, right, number that's being squared, actually when you use the shortcut method, which is what we're doing now, you actually need to ignore that negative, right, and only just drop the number, right? So just drop the 3, and then everything is squared, right? Then you're still going to have plus, and then we'll do the same thing for the y components. We're going to drop the y, drop the plus sign, and then drop what's inside the bracket. And in this case, it's a positive number, so it's just 2, right? So basically what we're saying is that when we're using the shortcut method, if inside of our brackets we have a negative number, we actually have to ignore that negative, otherwise it's going to lead us to have an incorrect equation. Right, so then we finalize this by just squaring this entire bracket, right, and then we just need to evaluate this other side. So on your calculator, if you evaluate 87 plus negative 3 squared, which is just basically plus 9, and then plus 4, right, you get that this is 100. Right, so now we can put back up here that this equation of the circle is basically equivalent, right, to the form x minus 3 all squared plus y plus 2 all squared is equals to 10. So is equals to 100. And then since we're looking for the coordinates of this point F, which is at the center, we can now get those coordinates directly from the equation. Remember that now we just need to change the signs, right, as we move outside into the coordinates. So we're seeing a minus 3 over here, so that makes this a positive 3 as an x value over there. And then we see a positive 2 over there, so it makes this a negative 2 as a y value. Okay. Just want to make things a little bit more clear. Alright, I rubbed it off unfortunately. We've got the point F over here, right, which is the center of this larger circle. Okay. Right, question 4.3, they're asking us exactly what they asked us in question 4.1. They want us to write down the length of the radius of the circle now centered F, right, and we know that we take that from the equation, right, basically the equation in this completed square form, we know that this 100 is talking about r squared, right? So the length of the radius, just r, is the square root of 100, which is 10 units. Okay, so 10, you can write here capital letter R is equals to 10 units. Okay, so let's just put that in the sketch over here. This capital letter R is equals to 10, and we calculated in 4.1 that the small letter r is equals to 5. Let me remove this because I might just need more space for the next question. Question 4.4, right. We now need to show with calculations, that h is equals to the square root of 104 minus 2. Okay, so where does this h come from? Well, it basically comes from the equation of the circle centered at M, right? That equation right over there. Okay, so if we look at this equation, we know that this equation is saying that the coordinates here at M, right, are basically change the sign, right? X value 14, y value, change the sign, h. Okay, so we have that the coordinates at M is 14h, right? Now they want us to show that h is actually equals to this number over here. Well, we can easily do that because we now know what is the distance between the two centers, right? That is obviously a distance of 15. Okay, the distance between these two centers is 15 units. Okay, we just calculated the coordinates at F, and we now just sort of like written down an incomplete form, right, of the coordinates at M, and we are just trying to show what the value of h is supposed to be. Okay, so what we can do is we can set up the equation and say that the distance Fm, right, let's talk about the distance Fm is going to be equals to the square root, right, of the difference in the x values. So let's start here at M. So x value is 14 minus the x value at F is going to be 3, and that has to be squared, plus the difference in the y values, that's going to be the h, minus the the y value here at F, which is negative 2. Right, and that whole thing squared. Okay, so as we determined, right, the distance Fm has to be 15 units, and this is equals to the square root of 14 minus 3 is 11 squared, and then we're going to have plus h plus 2 in brackets, and that is still squared. Okay, we're trying to get to this h over here, so it's going to be necessary for us to get rid of this square root, so that's easy to do. We're just going to square both sides. Right, and then in doing that, we get that we have 15 squared, which is going to be 225. And that must now equal 11 squared, which is 121, right, plus h plus 2 all squared. Okay, I'm not going to simplify that. Right, so if we now subtract 121 from both sides, we'll get the 104. Okay, that's looking good. And this is now equals to h plus 2, everything squared. Okay, now notice that basically this h, right, or this expression h plus 2 has to be such that it is a positive value, right, since h, right, is on the positive y-axis. Okay, so then it makes sense that we are just going to be looking at the positive square root of 104. Okay, just the positive square root, and that's going to equal h plus 2. Okay, so then finalizing from there, we get therefore h is equals to the square root of 104 minus 2. Okay, and we're done because we've now answered the question and we've shown with a calculation that h is in fact equals to that value right over there. Okay. So maybe we can substitute it in over here in our diagram. Right, so the square root of 104 minus 2. Question 4.5. It says, show that again, right, the equation of the tangent Jn, right, is equals to this, or is this, if J is given as the coordinate minus 3, 6. Right, so we now have that the coordinate of J is given to us as minus 3, 6. Okay, so what are they saying? They're saying that Jn, right, this is a tangent. Right, so now because we are in analytical geometry, we know that basically what we have here is this relationship of the tangent being perpendicular to the diameter of the circle. Right, this line JK is the diameter because it's passing through the center F. Right, so we know that we have that 90-degree angle there at that point of contact. Right, so the most important thing for us is that now we recognize that we have perpendicular lines, so we can most definitely find the gradient of the tangent by taking the negative reciprocal, right, of the gradient of the diameter. Right, so let's find out what is the gradient of the diameter JK. Right, we actually do have the coordinates at K, and we've now been given the coordinates at J, so this is actually a simple task to do. Right, let's start here at K. Let's take a difference in the Y value, so minus 10 minus 6 divided by difference in the X value, so 9 minus negative 3. Right, that gives you negative 16 divided by 9 plus 3, which is going to be 12. Okay, and then this simplifies to negative 4 over 3. Okay, so that's the gradient of the diameter. Right, so then therefore we can say that the gradient of the tangent, which in this case we're just going to call it Jn, okay, that is going to be equals to the negative reciprocal of this, so it has to be 3 over 4. Okay, so now we have the gradient of the tangent. We need a point that lies in the tangent, and that is always that single point. Right, so it is going to have to be this point J. Okay, so we're going to go into the equation y minus the y value of J is equals to the gradient of Jn times x minus the x value at J. Right, so we have y minus 6 is equals to 3 over 4 into x. We're going to have a double negative, so let's just go straight into writing this as plus 3. Okay, so simplifying here, we have y minus 6 is equals to 3 over 4x. Right, and then we're going to have 3 over 4 times 3, which is 9 over 4. Okay, and then I'm going to carry on up here. We now have y is equals to 3 over 4x plus 9 over 4 minus, plus 6. Okay, but we can now write this as something over 4, so 6 times 4 is 24. So simplifying one last time, we get y is equals to 3 over 4x. Okay, now the denominators are the same over here, 4. And then we're going to have 24 plus 9, which gives us 33. Okay, so we've now successfully shown exactly that equation that was given to us. Right, on to the last question, question 4.6. We have that a line, right, NL passes through the center M such that NL is parallel to JK. Right, so we have this line NL, right, which is parallel to the line JK. Right, so we already know what is the gradient of the line JK, so which means that we can easily take that gradient over if we need to. Okay. What else do they say over here? They say that the circle, right, which is centered at M, is translated along the line in L, right, between the two tangents of the circle F. Okay. For a given interval, right, x an element of PQ, right, we need to give the minimum value of P, right. So in this interval, P is actually the minimum value. So what they're actually just trying to say here is calculate the value of P, right, such that the circle M will not intersect the tangents of the circle centered F when translated along the line in L. Right, so this is a long story just to say that what you're doing is that you're taking the circle centered at M and you're moving it along this line. Right, so imagine having this point M moving maybe to say somewhere over here. Right, then you can see that when it's here, right, then you'll have a new position of the circle. Right, so if we try to estimate the new position of the circle, right, after translating this point M along the line NL, right, it should be something like this. Okay, and basically what I've drawn right now is exactly what we're trying to figure out, right? It's our desired case, right? The case where when you translate this circle, you have it not actually intersecting the tangents, right? So if you're not intersecting the tangents, it means that you are at least touching the tangent at one point, right? So basically the tangent of this larger circle also then becomes the tangent of the smaller circle. Okay, so what is the goal over here? Well, the goal is to find, right, really what is this x value, okay, that basically when we have that x value, we're going to have this circle M, right, being translated to the point that it is actually now tangential to the tangent Jn. Okay, so we're looking for what is that p value over there. Okay, that minimum p value. Right, so you can see now that what we have there is a point of intersection between two lines, right? There we have the intersection between the tangent, right, Jn, and the diameter, or just this line. It's not actually the diameter. The line, right, NL. Okay. Right, so the first thing we can do is to find out what is the equation, right, of the line NL. Okay, so we're going to write over here that what we're doing now is we want to find out what is the equation of NL. Okay, the first thing we know is that NL is parallel to JK, so then the gradient of NL is equal to the gradient of JK, which we calculated as negative 4/3. Okay, if you can remember that. Now let's go into the equation. Y minus the y value. We need a point that is on the line NL. Well, the only point we really have is this point M. So it's going to have to be the y value at M is equals to the gradient of NL into x minus the x value at M. Okay, so if we substitute this in, we're going to have y minus, well, the y value at M is the square root of 104 minus 2. That's equals to negative 4/3 into x minus, and the x value there is 14. Okay, so let's clean this up a little bit. We're going to have y minus the square root of 104 plus 2 going to equal negative 4/3x, and then we're going to have plus 4/3 times 14, which is positive 56/3. Okay, so you can just write this as, therefore, it's going to be an unusually looking equation. y is equals to negative 4 over 3x plus 56 over 3 plus the square root of 104 and then minus 2. Okay, it's a very unusual equation, but let's just leave it in that form for now. Right, so I've noted our result on screen over here, right in this box. That is the equation of the line in L. Okay, since we've noted that this point over here, right, is a point of intersection, right, just a single point of intersection, what we want, okay, is to then basically set the equation of the tangents, which we have already, right, we've already shown it in question 4.5. We want to set basically now the equation of the tangent, which is Jn, right, equal to the equation of the line that we just calculated now, okay, the equation of NL. Okay, so therefore that is going to be 3 over 4x plus 33 over 4. That must equal negative 4 over 3x plus 56 over 3 plus the square root of 104 minus 2. Right, so if you punch all of that into the calculator, you get that to 2 decimal places, right, that x value has to be 8.94. Okay, so you can finalize this by just saying that this is also then equals to the value of P. And that then takes care of question number 4, right? So what have we done so far? We've covered the theorem, right? We've done statistics, and we've now covered the entire analytical geometry. And it's taken us quite a long time, right? So we need to pick up some ground here. So I think it is best to then move on to the functions, right? So we're going to skip question 5. We'll come back to it. Let's move on to the trigonometric functions, which is question 6. Right, so let's see what we have here in question number 6. We have that in the diagram below, we have the graphs F and G. Right, so F is the sine graph, so let's just color code it. I am going to color code F as a green graph, so this is the graph of F. Right, and then we also have that the graph of G is a tan function, right, so I'm going to color code that as a blue function, so that's basically this function over here. Right, so what type of transformations do we have over here? They're not really that major, right? For F, we only have some amplitude, right? We have f of x is equals to a sine of x, and for g of x, right, we just have a change in period. We're looking at g of x is equal to the tan of bx, right? We're obviously then going to have to figure out what is that value of a and b, okay? And these two things are drawn for us, right, in the interval between minus 180 degrees, right, all the way up to 360 degrees. Okay. What else do we have? We have that the point P, which is 90 degrees 3, is on the graph of F, and the function h of x is equals to 3 over 2 intersects the graph of F and G. Okay, so we have this function h over here, so that basically has the equation y, or h of x is equals to 3 over 2 or 1.5. Okay. Lastly, we have that the asymptote of G, right, one of the asymptotes of G, basically the one that is shown to us over here, it goes through one of the turning points of F, right, so they're talking about this turning point over here, and we know that basically this is just a normal sine function, we just have a change in amplitude, so all our key points, right, haven't changed. This is still 0 degrees, right, that's 90, this is 180, So then this is 270 degrees. Okay, so basically what they're saying is that we have an asymptote of G, right, going through the point 270 degrees. Okay, we have A and B, right, and we are given the coordinate of B. These are the points of intersection between the two graphs F and G. Okay, so there's A over here, if you can't see it, and there is B hiding right over there. Okay, so let's see what the questions say. Question 6.1 says write down the values of A and B. Right, so A, like we said, is related to the graph of F, and that is talking about the amplitude of the sine graph. Amplitude, you will find it at either your maximum or your minimums, right? And the only maximum that we really have is this point P. We see that the y value there is 3, so thus the amplitude is 3. Okay, so then we can just write down that A is equals to 3. Okay, now what about B? Well, for B, you wouldn't really be able to write this down. You have to go through some sort of a calculation, right? And the calculation that I like to use is the one that says that the new period of your graph, right, since B controls the period, is going to be equals to the original period right, divided by that B value. Okay, so then if I rearrange over here, if I times by B on both sides, the B will cancel out here and will appear on this side, so then therefore B is going to equal the original right period divided by the new period of the graph. Okay, so what is the original period of a tan function? Well, that's 180 degrees. What's the new period? Well, we can get it off from here, right? We can see that this tan function, if we had to expand this out, right, we know that the next point over here, we would have then a second asymptote, right, at negative 270 degrees, right? So then basically this graph is taking 540 degrees, right, in order to complete a full cycle. And this is the full cycle of the tan graph. I am going to draw over it. Right, so that's one full cycle of the tan graph. Okay, so if you plug this into your calculator, you get that B is equals to 1 over 3. Okay, and another way that you could have figured out that B value, and I learned this from one of my subscribers, right, is to just look at the old coordinates divided by the new coordinates, right? And specifically over here, what would help you is this coordinate of your asymptote, okay? So you would say that B is equal to the old coordinate of the asymptote, and you need to know the original tan function, right? And you would know that it reaches its first positive asymptote, right, through x is equals to 90 degrees, right? So that would be the old position of the asymptote. And now you can see that the new position of the asymptote is 270. Okay, so if you simplify this in your calculator as well, right, you still get that B is equals to 1 over 3. Right, so let's move on to question 6.2. It says, write down the period of G. Well, unfortunately, I already sort of like calculated it before, right? The period of G, the way that I found it is I took 270 degrees minus negative 270 degrees, and that's how I found that the period of G, okay, is equals to 540 degrees. Okay. Question 6.3. Write down the coordinates of A. Alright, so the coordinates of A is going to be this point over here. Right, A is related to B, right? those 2 points are the points of intersection, right? So then basically it is going to be sort of like a reflection of this point B, okay, from the first quadrant into the third quadrant. Right, so the only thing that would have to change when we do that reflection is just a change in sign, right? So in the first quadrant we've got positive y, positive x, but in the third quadrant we've got negative x and negative y's, right? So we just need to then change the signs over here. So this is going to be negative 154.69 degrees, and then we're going to have negative 1.28. Right, so on to the last question, question 6.4. Okay, we have that it is given that 2 tan of 56.31 degrees minus 6 sine of 168.93 degrees is equals to t plus 5. Calculate in terms of t the vertical distance between F and G at the point where H intersects G. Okay, right, so this is kind of an odd question. Don't really know what it would be related to, but it is more just following sort of like procedure, right? If you can at least figure out where to start and then somehow find the connection between what's given, you will get to the answer, right? But this is just one of those weird questions that have no connection whatsoever to anything, right? Other than showing that you know how to work with algebra, okay? All right. So what can we use over here? Well, the only thing that we really can use is the fact that we are basically trying to calculate the vertical distance between F and G, and we're given a condition that we specifically want that vertical distance at the point where the graph H intersects G. Okay, so here's the graph H, right? It's this horizontal line. Over here, it's intersecting F. Over there, it's intersecting F. But over here, it's intersecting G, right? So we are looking for this vertical distance. Okay. Right. Now remember that the graphs are not necessarily drawn to scale, so let's rather not assume that that x value, right, is 180 degrees. Okay, it looks like it, but let's not assume it. Okay, let's try to figure out what is that x value, right, where this vertical distance actually exists. Okay, let's first actually deal with this vertical distance. Well, the vertical distance is going to be given by the graph that's on top, so g of x minus f of x. Okay, so that is going to be g of x is, let's just remind ourselves, that's the tan graph, so that is going to be the tan, and we now know that b is 1/3 x. And we're subtracting from this f of x, which is now 3 sine of x. Right, so this is just basically the expression, right, for the vertical distance. It's not actually going to help us to find that vertical distance. What we're really trying to find out now is to sort of calculate more accurately where is that x value for this vertical distance. So we're going to have to find something else to help us out, and that could be the equation that we can form by noticing that over here what we have is a point of intersection. Okay, so point of intersection. Okay, between what? Well, between g of x and h of x. Okay, so we can use this equation, right, to figure out what is that specific x value. Okay, so g of x is the tan of 1/3 x, and that equals to 3/2. Okay, so you can see how this can now help us to find out what is that x value, right? So our reference angle right, is going to be shift tan of 3 over 2. Okay, and that gives us 56.31. Okay, we are in the first quadrant here, so we're only really just interested in a positive solution, right? So we're not going to really need to use anything else but this reference angle. Okay, so then we can say that therefore 1/3 x is equals to 56.31 degrees. Okay, so then therefore x is equals to, still in my calculator, just need to divide that by 1/3, and we get that the specific x value where this vertical distance exists, right, is at an x value of 168.929898 degrees. Okay. Alright, so if you look at this to 2 decimal places, which is 168.93, you can see all of a sudden there is that angle over there. Okay, and also we have that angle of 56.31 over here. Okay, so now we're seeing a connection between the angles that we've calculated and the given statement. What we've written above is an expression that determines the vertical distance, right? So this is an expression that determines the vertical distance. Okay, so how do we move forward from here? Well, we move forward basically by then saying, well, if these angles that are showing up over here are in the given statement, then it means that we need to substitute this x value into the expression that determines the vertical distance, right? So then therefore, we're going to be looking at the g of 168.93 degrees minus the f of 168.93 degrees. Okay, so into the other side, that's going to be the tan of 1/3 times 168.93 degrees, right? But this 168.93 is basically x, so then this is just 1/3 of x, so we know what 1/3 of x is. That is basically the tan of 56.31 degrees. Okay, and then we've got minus 3 times the sine of 168.93 degrees. Okay, and that doesn't change in the next line. Okay, so now if you compare what we have over here with what was given, right, you can see that the odd things out is this 2, right, and this 6 over here, right. We have a minus 3, they have a minus 6. Right, so we can now then say that it was given, right, so it was given that 2 tan of 56.31 degrees minus 6 sine of 168.93 degrees is equal to t plus 5. Right. Now we notice that this first part is related to the vertical distance. What did they want us to do? They wanted us to calculate the vertical distance in terms of t. This is the only place where t shows up, so we need to now make this part of the given equation look exactly like what we have above, right? And we can do that by taking out a common factor of 2. Right? So if we take out that common factor of 2, we're going to have the tan of 56.31 degrees minus 3 sine of 168.93 degrees, and that must equal t plus 5. Okay, so then therefore the tan of 56.31 degrees minus 3 sine of 168.93 degrees is equals to t plus 5 divided by 2. Okay, what was this? Well, it is the vertical distance. So therefore we've now determined, therefore that the vertical distance can be given by the expression t plus 5, all of this divided by 2. Right, and for my visual learners, right, I just noticed that I've let you down a little bit here. Okay, so if you go back to the sketch over here, right, we're talking about a vertical distance between F and G. So in fact, I wasn't supposed to make this line, right, continue downwards, because then it's no longer the vertical distance between F and G. We're basically just looking at this vertical distance like that. Okay, so there is G, and then here is F. Okay, so just that distance, right? And what we did is that we calculated that that vertical distance, right, lies at the x value of 168.93 degrees. We took that angle and substituted it back into the expression, right, which determines the vertical distance, right? And then from there, we then saw the connection between that expression and what was given to us. And then we basically then conclude the vertical distance in terms of t. Okay. Alright, so with that, let's now move on to question number 7. Okay, in question 7, we have that the diagram below, we have still poles AF, DB, and CE, which are all equal in length. Okay, and they are vertical to the horizontal plane FDE. Okay, the still poles hold the triangle ABC that forms the roof of a storage area. G is the midpoint of DE, and BCDE is in the same vertical plane. Okay, AB is equals to AC, which are both equal to X, and BD is equals to Y, and the angle BAC is equals to theta. Okay, so all of that is indicated on the diagram except the fact that these still poles AF, right, BD, and CE are all equal in length. We know what the length of BD is, that's Y, so that means that we have a Y over here and a Y over there. Okay, and since these things are vertical, we know that they are always going to form a 90-degree angle with the ground. Okay, right, 7.1. Okay, we need to show that BC, okay, so there's BC, is equals to this, right? So BC is basically in that roof, right? So the triangle ABC, so in triangle ABC, okay, we can see that BC is the side opposite an included angle, right? We have the length of these two including sides, AB and AC, both of them are equal to X, so we can then apply the cosine rule over here. Okay, question 7.2, right, says write down the size of the angle BDG, right, so BDG, right, so this angle over there, right, BDG. Well, we already identified that that is an angle of 90 degrees, and that basically comes from the theory that says that any vertical object, right, is always perpendicular to the ground. What we say is that it's always perpendicular to the horizontal plane. Okay, and this shaded area is our horizontal plane. So then therefore we say that the angle BDG is equals to 90 degrees. Question 7.3 says show that BG, right, so that distance there, BG, is equals to this. Okay, so BG now lies in this right angle triangle BDG. Okay, so we can use the theorem of Pythagoras in there. Okay, so we have that BG is the hypotenuse, so we're going to have BG squared is equal to the sum of the other two sides squared. So we're going to have BD squared plus DG squared. Right. This is our famous Pythagoras. So what do we know? We do know that DG, okay, so DG, okay, is basically half the full length DE. Okay, so now let's go back to the given information. They tried to point out to us over here that this figure BCED, right, is in the same vertical plane. In other words, it's standing like upright, like a wall. Okay, so it's basically like a yeah, it is. If this is a storage area, you can think of this as like sort of like the back wall. Okay, so it is perfectly vertical, right? So then if it's perfectly vertical, then geometry basically forces that this figure BCED, right, has to be a rectangle, right? In other words, we have to have a 90-degree angle over there, 90-degree angle over there, and obviously now the properties of the rectangle come in. DE, right, is equals to BC, right? The properties of the rectangle basically say that the opposite sides, right, are equal in length. So we can write here but, and then we can say therefore DG is equals to half, right, of BC. Okay, and we just showed what the length of BC is in the previous question. Alright, so now putting all of these substitutions together, going from this equation, right, so going from this equation, we now have that BG squared, right, is going to be equals to BD squared. BD was given to us as Y, so that's Y squared plus, DG squared. So DG, we're first going to substitute in a half, okay, of BC, and BC is x square root of 2 into 1 minus the cosine of theta. Okay, don't forget that still has to be squared. Okay, so from here we're now going to have that BG squared is going to equal Y squared plus, right, now if we square everything inside of this bracket, if you square the 1/2, you're going to get 1/4, okay, and if you square the x, you're going to have x squared. If you square the square root will cancel out, leaving you with times 2 into 1 minus the cos of theta. So what's going to happen now? Well, this 2 will cancel out at one of the 2's in the 4. So we'll have that BG squared is equal to Y squared plus a half this time, x squared into 1 minus the cosine of theta. Okay, so let's just look at where we are going. Is it a nice thing that we have an x squared? Yes, I can see an x squared over there. I can still see this term 1 minus cosine of theta. Okay, I see a 2, right, but it's sort of like distributed over these two things. So basically what they've done now is that, let me just rewrite this so that you can see what's going on. We basically now have two fractions. Okay, so if I rewrite this as just x squared into 1 minus the cosine of theta, all of this divided by 2, like that. Okay, instead of having the half outside by itself. Now you can see that basically what we have is two fractions that need to be added together. So we need a LCD over here of 2. So this is going to be 2 over 2. Okay. Then to finalize, okay, we just need to take the square root of both sides. So then BG is going to equal the square root, okay, of 2y squared plus x squared into 1 minus the cosine of theta. And the denominators are the same, so we can put that over the same denominator of 2. Okay, now if you compare this to what you have to show, you have that 2y squared plus x squared into 1 minus the cosine of theta, everything divided by 2, and then everything square rooted as well. Okay, so last question, question 7.4, sorry. Okay, it says it is given that y is equals to 8 over 3 meters and x is equals to 15 over 2 meters. Calculate the maximum length of BG. Okay, so we just basically showed an expression that determines the length of BG. Okay, now if you look at the expression, you are basically going to be substituting in that x value and that y value. So which means that in order for you then to find out what is the maximum length, it's all going to be dependent on this part of the expression, right? The 1 minus cosine of theta. Okay, so then you're going to write over here, okay, that therefore the maximum length of BG is dependent on the maximum of 1 minus cosine of theta. Right, so if we can determine what is the maximum of this, right, substituting that maximum is together with these x and y values will then give us the maximum length of BG. Okay, so this now takes you back into the functions, right? So let's start off with just the cosine function, right? We know that it looks like that. Okay, this is the cos of theta. Now let's look at minus cos of theta. Right, so minus cos of theta basically just reflects about the x-axis. So it's going to start down here. It's going to go up like that. And then it's going to do that. Okay. So now we've dealt with the minus cosine of theta. This is minus cosine of theta. We now need to just add 1 to it, which is basically moving this graph 1 unit upwards. Okay, so if you move it 1 unit upwards, it's going to look like this. Okay, so now this is 1 minus the cosine of theta. Okay, so let's put in our values. We know that this maximum was originally at 1. Okay, if we tip it over, it then becomes negative 1. Okay, now the negative 1 shifted 1 unit upwards puts it at 0. Okay, okay, that still hasn't helped us to find that value there at this maximum. This is our goal. Right, so let's go back to the start. We know that over here, at this minimum, right, that happens at negative 1. Okay, so when you flip it over the x-axis, that goes to a maximum at 1. Okay, and then that maximum at 1, if you move it 1 unit upwards, it will go up to a maximum at 2. So I'm going to carry on over here. So then we're going to say, therefore, 1 minus cosine of theta is a maximum, not really is a maximum, let's say has a maximum value of 2. Okay, so then therefore substituting all of this in, BG is going to equal the square root of 2 times y squared, 8 over 3 squared plus x squared, which is 15 over 2 squared, and then that whole expression has a maximum value of 2, so we substitute in 2, and all of this underneath the square root is divided by 2. Let me just fix my square root. Okay, so if you plug all of this into your calculator, you get that the maximum length of BG is equals to 7.96 to 2 decimal places units. Right, so now let's not forget that we actually did skip one question so far. So let's go back to that question. That was question number 5. Okay, so that will then now conclude the trigonometry. Okay, so let's go back to question number 5. Right, question number 5. It says, in the diagram, right, P is the coordinate, or P has the coordinates K1, right, is a point in the second quadrant, okay, and is square root 10 units from the origin. Okay, all of this is already shown on the diagram. Okay, T is a point on the positive x-axis, and the obtuse angle POT is equals beta. Okay, we can actually now start identifying that as an angle of inclination, but this is trick. But we might use it, we might not use it. Let's just keep it at the back of our minds. Okay. Alright, so question 5.1.1 says calculate the value of k. Right. So the value of k is the x value at that point P. Right. So when you have these diagrams, it is always recommended that you actually drop down the perpendicular, okay, so that you can see that what you're dealing with here is actually a right angle triangle. Okay, that distance that they want you to calculate now is a distance k. The distance upwards is a distance of 1. Okay, and you are given that, let's write in that k, right, you're given that the distance of the hypotenuse basically is the square root of 10. Okay, so now you can see that you can use the theorem of Pythagoras here to evaluate this value of k. Okay. Alright, so what does that say? You can basically say k squared plus 1 squared, right, so these are the two sides squared, must equal the hypotenuse squared, right, so the square root of 10 squared, right, and this is our friend Pythagoras. Okay, alright, so from here we're going to have k squared plus 1 is equals to 10, right, so then therefore k squared is equals to 9. Okay, here you can actually write out that k is equals to plus and minus 3, and then conclude that therefore k is equals to minus 3. You can write here, since P is a point in the second quadrant. Okay, that's one way that you can set this out, right? So then this then allows us to then make a substitution here for that k as minus 3. Right. Question 5.1.2, okay, part A. They say calculate, right, without using a calculator, the value of the following. Okay, you're looking at the negative cosine of theta. Okay, alright, so for this one, notice that this angle theta is basically an angle in the second quadrant, right? So we can sort of like start off from the reduction formula and talk about the cosine, right, of 180 degrees minus theta. Okay, we know that 180 degrees minus theta is an angle in the second quadrant, right? This reduces down into negative cosine of theta, which is exactly what they want us to calculate. Okay, so then that means that we can actually use this diagram, right, to evaluate this. So we're going to have negative, right, and cosine is basically x over r. Okay, and we know that the x value there in this triangle is -3, and the r value is the distance of the hypotenuse, which is square root 10. I need my brackets there. Okay, so this is then basically equals to 3 square root 10, or you can rationalize this and write it as 3 root 10 over 10. Okay. For part B, right, we see we have a bunch of reduction formulas in here. So let's just simplify in here. 1, okay, 180 degrees plus theta is in the third quadrant, right? Sine is negative in the third quadrant, so this reduces down into the negative sine of theta, okay? And this is times, right? 360 degrees is in, 360 degrees minus theta is in the fourth quadrant, right? Sine is still negative in the fourth quadrant, so this thing reduces down into negative sine of theta, like that. Okay, so if we carry on simplifying over here, we still have our 1 minus, okay, and then we've got this product. So negative times negative is positive, and sine theta times sine theta is going to be sine squared of theta. Okay, we've all recognized this identity before. This is equivalent to cos squared of theta, and now you have a squared and a square root, and that must cancel each other out, so that must equal the cos of theta. Right, now don't now overcomplicate things for yourself. You just calculated that the negative cos of theta is equals to 3 root 10 divided by 10, so then the cos of theta must then equal negative 3 root 10 over 10. Okay, question 5.1.3 says, show without using a calculator that the sine of theta over 2 is minus 15 degrees times the cosine of theta over 2 minus 15 degrees is equals to all of this. Okay. Alright, so the trick over here is really just to recognize the fact that you have this pattern sine times cos, right? And in essence, the important thing is the fact that your angles are the same, okay? So we can then draw from the double angle of sine, right? So we know that the sine of 2 alpha is equals to 2 sine alpha cos alpha. Okay, so what we are given is this component over here. So this sine times cos with the same angle. Okay, so we can rearrange this to have this as a half sine of 2 alpha is equals to the sine of alpha cosine of alpha. Okay, so now if we are given this, we are now going to work backwards and create this part over here. So this is going to be equals to a half sine of 2, and our alpha in this case is this bracket theta over 2 minus 15 degrees. Okay, so if we simplify here, we're going to have a half times the sine of, if you distribute the 2, you're going to have theta minus 30 degrees. Okay, right, so now grade 12, what do we see over here? We now see a compound angle. Okay, this half is still sitting outside really, so let's do that. If we expand this, we know that we're going to have sine theta times the cosine of 30 degrees minus the cosine of theta times the sine of 30 degrees. Okay, notice the numbering. This is question 5.1. We are in question 5.1, 5.1.3, right? So this theta is still related to this triangle up here. Okay, so don't now freak out and worry about how you're supposed to figure out what is the sine of theta. You then use the triangle again. Alright, so if we substitute into here, okay, it is then going to be useful to substitute in the unrationalized form of our surds, okay, so that the answer can come out exactly the way it's given over here. Okay, so let's substitute in. We're going to have a half into the sine of theta will come from the triangle, which is going to be 1 divided by the root of 10. Don't rationalize this. Okay, this is times the cosine of 30 degrees is the root of 3 over 2. Okay, minus the cosine of theta, and if you don't rationalize that, that is going to be negative 3 divided by the root of 10. Okay, and then the sine of 30 degrees is 1/2. So the trick to this question was really to substitute in the sine of theta, okay, the sine of theta and the cosine of theta in this form, right, where you have the square roots in the denominator. Okay, so in other words, don't rationalize those denominators, right? Right, now we can move on swiftly to question 5.2, and in question 5.2 we now are in our general solutions. Okay, so this one is quite a simple one, so let's get to it. Alright, so we have that we are given, right, whenever we're given something, we're most definitely going to use it. So we are given that the sine of theta plus 60 degrees is equal to d. Okay. Question 5.2.1 then asks, write down the values of d such that the sine of theta plus 60 degrees is defined. Okay. Right, so let this d not throw you off. We could have easily called this the sine of theta plus 60 degrees is equals to f of x, right? Or equals to y, right? So let the d basically not confuse you, right? So we can basically answer this by thinking about the sine function, right? When is the sine function defined? Well, the sine function is only defined within its range, okay? So if they want you to write down the values of d, right, for which the sine function is defined, well, it is going to be the values of d, which are going to be between -1 and 1, right? So this is the range of the sine function. And why does it stay constant between -1 and 1? Well, because we don't have any change in our amplitude, right? So we don't have any a value over here. Our a value is equals to 1. So then the range of this function, sine of theta plus 60 degrees, is going to be exactly the same as the range of the function sine theta. Okay. Right. Question 5.2.2 says if d, right, so if d is equals to the sine of theta times the cosine of 60 degrees plus the square root of 3 over 8, right? And the general solution, right, of sine of theta plus 60 degrees equals to d, right? So in other words, when we have this equation, sine of theta plus 60 degrees equal to d, and we're now given some expression to assume for d, right? Sine theta times cos 60 degrees plus the square root of 3 over 8. Okay, they're saying that when we have this situation, right, the general solution is such that theta is equal to plus or minus m degrees plus n 360 degrees, right? We need to calculate without using a calculator the value of m, right? Now, the tip that we have over here is that we are told that this, okay, that is the general solution, and we have this plus and minus over there. Okay, now we know that the only general solution that actually has a plus and minus sign in it is the general solution that results from cos. Okay, so we now know that basically that direction that we need to take here is to reduce all of this. Okay, we need to reduce all of this down to just having cos. Okay, so let's see how we can do that. We have sine theta cosine 60 degrees on both sides of the equal sign, right? So this term is going to cancel out, right? And that's going to leave us with the cos of theta, right? Now notice what I said. I said that looking at this general solution, because we have that plus and minus sign over there, right? We know that we eventually have to evaluate a general solution of cos. Okay, so which means that we are going to have to write down the value, right, of sine of 60 degrees. Okay, now the sine of 60 degrees is equal to the square root of 3 divided by 2. Okay, now all of this is now equals to the square root of 3 over 8. Okay, so we can now simplify this further and write this as the cosine of theta is equals to. Okay, so if you plug that into the calculator, you will get root 2 divided by 2. Okay, so root 2 divided by 2. All right. Oopsie, check here. They said without the use of a calculator. Ah, damn it. Okay, so let's just fix that quickly. Alright, so we know that if they say without the use of a calculator, we basically need to show all of our steps. So it is technically incorrect for us to go straight into writing this answer. We would have to say, right, the square root of 3 over 8, right, which we know is basically the same thing as the square root of 3 divided by the square root of 8, okay, and then that has to be further divided by the square root of 3 over 2, or just multiplying by 2 divided by the square root of 3. Okay, now the 3's cancel out, leaving us with the cosine of theta is equals to 2 divided by the root of 8. We can rewrite that as 2 times 2 squared. Okay, so then that will then simplify further into the cosine of theta is equals to 2. And inside over here, we can't take the square root of 2, but we can take the square root of 2 squared, that is 2. So we're going to pull that out, and we're still left with the root of 2. Okay, now the 2's will cancel, leaving you with cos of theta is equals to 1 over root 2. Alright, and then from here, if we rationalize this, right, by multiplying top and bottom by the square root of 2 divided by the square root of 2, then we will get that answer that we obtained from the calculator, which is root 2 divided by 2. Okay, alright, so now we obviously know that theta from here is then going to be equals to, it is plus or minus shift, right, root 2 over 2. Okay, this is basically asking which angle, right, you can see there m degrees, which angle, right, is going to have the value root 2 divided by 2. Okay, and then we usually say over here plus k 360, but they are using the variable n, right, not k, so we'll write here plus n 360, and they are actually missing in an element of integers. Okay, and just to quickly clarify what just happened now, right, I basically just applied this theory, right, so this theory over here, that first states that if a, right, this output value is positive, right, is it positive? Yes, in our case it is positive. Okay, and that a value is within the range of the cosine function, right, between -1 and 1. The square root of 2 divided by 2 is between -1 and 1. It's approximately 0.7. Okay, that's another condition that it meets, right? Then the theory says that when you have this setup, okay, cos of theta equals to a with these two conditions met, right? Condition 1 met and condition 2 met, okay, which is what we have right now. Then what happens is that theta is equals to directly just plus or minus shift cos of a, and then obviously plus k 360, but in our case we're looking at plus n 360. These things are just dummy variables, right? The k and the n are just dummy variables, okay? Right, so if you were confused about what happened over there, we basically just applied this theory. Okay, so all that's left now is for us to identify this value of m, right? And basically the value of m, if you can look at it, is going to come from evaluating what is shift cos of the square root of 2 over 2. Remembering also that they told us not to use our calculator, but obviously what they're trying to do here is to hopefully get you to remember that this is one of our special angles. Okay, if we just recall our special angles quickly. Right, we've got 0 degrees, 30 degrees, 45 degrees, and 60 degrees, and 90 degrees. Right. This setup of root 2 over 2 is right here at 45 degrees. Right. We have root 2 over 2, root 2 over 2 as the x and the y coordinates at 45 degrees. Okay. So now that we've identified that, we can basically answer this question and say, therefore, theta is equals to plus or minus 45 degrees, because if you take the cosine of 45 degrees, right, that's what gives you the output root 2 over 2. Okay. Then we just add all of these other things. Okay. And then lastly, answer the question. Therefore, m, right, is equals to 45 degrees. Like that. Okay. Right, now question 5.3 is one of those funny questions, right? What we call higher level questions. But this one specifically, it's not so extravagant, right? You don't really learn anything wonderful from it. It all just depends on where you're able to identify this in the exam, okay? Because chances are under pressure, you might have not been able to see this, okay? So let's just scroll to the side. This is for 3 marks, okay? So I had to zoom into this a little bit so that you can see. Right, so what we have here is that we have we can call it a function if you want to, a, right, which is equals to 2 with an exponent of sine of, look at that, sine of a minus m times sine of b minus m times the sine of c minus m all the way up to the sine of x minus m. Okay, so now obviously in order for you to be able to answer the question, which is to calculate the value of a, you obviously then need to evaluate that exponent. Okay, now if you look at this, right, you might be tempted to start thinking about your series, okay, but notice that we don't have plus or minus signs here, so this is not a series. This is a lot of products, right, because we're taking the sine of an angle a minus m times the sine of an angle b minus m times the sine of an angle c minus m all the way up to the sine of x minus m. Okay, right. Another thing that can confuse you here, or that can lead you to do lots of unnecessary calculations, is to see a minus m, b minus m, c minus m, and x minus m as a compound angle, and then try to expand that out. Okay, that is going to lead you nowhere. Okay, and also be guided by this. This is for 3 marks. So clearly there has to be something about this, right, that can be simplified quite quickly. Okay, so let's first check what is constant. Okay, so we are focusing here on the exponent, right? The first thing that's constant is that we are always multiplying by sine. Okay, another thing that's constant is that the second angle is always m. Okay, so what's changing? Well, what's changing is this first angle. We have an angle A, then an angle B, then an angle C, and then it goes all the way up to an angle X, right? But then realize the fact that if it's going all the way up to an angle X, then obviously somewhere along this multiplication string, if we can call it that, okay, we are going to have some product, right, somewhere in between here, that is going to be the sine of some angle M minus angle M, right? And that will go all the way up to, right, the sine of some angle X minus M. Okay, so now this over here, right, becomes the important factor. Okay, actually let's not write an equal sign, let's say but, okay, the sine of angle M minus M is going to be equal to the sine of 0. Okay, since M minus M is 0. Okay, now what is the sine of 0? Well, the sine of 0 is actually 0. Okay, now what do we have over here? We've got multiplication. Okay, so somewhere in this multiplication you are going to multiply by a 0. What do we know? We know that 0 times anything is 0. Okay, so that means that this whole gigantic exponent, right, is just a very complicated way of saying an exponent of 0. Okay, so then we'll conclude and say therefore a is equal to 2 to just the exponent of 0. Right, now this is now exponential laws, right? Any base to an exponent of 0 is always equal to 1. Okay, so then therefore a has a value of 1. And there you go. Right, then matriculants, we've now completed the trigonometry section of this paper. Right, so if you can remember, we started off with the we started off with the proof, right, the circle geometry proof. Then we went on to the stats. Then we went on to analytical geometry, and then we jumped into trig. Okay, so what's left is the last few questions of circle geometry. Okay, so let's just quickly scroll through this paper and see that we've actually covered everything, just to make sure. Okay, so we've done question 1, yes, question 2, question 3, question 4. We've just completed question 5. We did question 6, question 7, and so now we are here at question 8, just remembering that we've already covered question number 9. Okay, so let's see what question 8 has. The first instruction that we see over here is to always give reasons, right, for your statements. Okay, all right, so question 8, we have that in the diagram below, right, O is the center of the circle, okay, with radius OC, okay, OC, okay, there we go, OC. ABCD is a cyclic quadrilateral, okay, so A, B, C, D, okay, so just that figure over there is a cyclic quadrilateral. All right, N is another point on the circle such that ON is parallel to BC. Okay, so N, we're talking about this point over here, right? That's a point on the circle such that this line segment ON right, is parallel to this line segment BC. Okay. We have chords DN which are drawn, and we also have that OE bisects, right, the chord BC at E. Okay, so now this is telling us that E is basically a midpoint. Okay, so E is a midpoint. Okay, what else do we have? We also have that GC. Okay, where is that? There it is, GC, right, so this is a tangent, okay, to the circle at C, and then we also have that ON and GC are produced to meet at point F. Okay, all right. Lastly, we also have that angle OCE is equals to 20 degrees, angle OCE is equals to 20 degrees, and angle DAB is equals to 150 degrees. Where is that? Angle DAB. Okay, so that's already indicated for us in the diagram. Let's just quickly highlight for ourselves that cyclic quad. Right, so before we look at the questions, it is always good practice to then, now that you've read the given information, okay, now start interacting with the drawing, okay, and start thinking to yourself, okay, from the given information, what can I now deduce, right? What theorems can I see, right? What is the obvious things that are coming out from this picture, okay? Basically, you're trying to find the relationships, okay, that are existing in the specific rider, okay? All right, so let's just make this point E a little bit darker. Let's start there, okay? Now that I've touched this point E, we said that the point E, well, we didn't say that. We were told that the point E, okay, is the midpoint, okay, indirectly, right? We were told that indirectly, okay. Now, what theorem do we know, right? It's one of the first theorems that we have. It's actually the converse of one of the theorems that we have, right? And it states that if you have a line, right, coming from the center of the circle to the midpoint of a chord, right, our chord here being the chord BC, then that line is perpendicular to that chord, okay, so which means that we have a 90-degree angle over here. All right, what else can we take out of this picture? Well, ABCD is a cyclic quad, so we know that we can have some relationship between angle A and the full angle C, right? We know that the sum of those two angles has to be 180 degrees. That comes from this theorem that says that the opposite angles of a cyclic quad are supplementary. Okay, so we can definitely from there calculate what is angle C1. Okay, so let's do that quickly. We're going to have 180 degrees minus 150, which is going to be 30 degrees, and then minus a further 20 degrees is going to make this angle, actually angle C2, okay, to be 10 degrees. Okay, and if ever we are asked to find out what is that angle, then we know how we got there. Basically, we know the reason behind it. Okay, what else can we see? Well, we have a tangent over here. Okay, remember that we have a tangent GC, okay, which has been produced to F. So what relationships is this tangent creating? Well, we all know that we are going to be looking for the tan-chord theorem, right? And let's see. Okay, so let's start here with angle C4, right? So angle C4 is connected to the chord BC. What is chord BC subtending? Well, if you go from chord BC, right, and you travel to the circumference, you'll see that it's actually subtending angle BD2. Okay, so which means that angle C4 is equals to angle D2 by the tan-chord theorem. All right. Next, let's use the other side. Well, the other side, we have that angle C1. Okay, I'm going to show it like this with a line through it. Okay, angle C1 is basically connected to the chord DC, right? So now if you go from the chord DC and you travel to the circumference, you'll see that the chord DC subtends angle B2. Okay? So which means that by the tan chord theorem, angle C1 is equal to angle B2. Right, and then let's also not forget that one of the most primary theorems that we know is that a radius always connects with the tangent at 90 degrees. Okay, so they pointed out to us, okay, that the radius of the circle is the line OC. Okay, they pointed that out to us. It's important. Then it means that we actually need to pay attention to that. Okay, so here's the radius OC. Okay, I'm going to color it in green. We know that where it makes contact with the tangent, it forms a 90-degree angle. So we basically have a 90-degree angle over here. Right, it's going to be huge, but you basically get the point. And also it's going to be on the other side as well, but I'm not going to put that much information into the diagram. We do know that that 90-degree angle is on the other side as well. Okay, so which means that now we can actually calculate what is angle C4, and we know if we have to give a reason, right, once we look at the questions, we know what our reason is going to be. Right, the reason is going to be radius perpendicular to tangent. Okay, so 90 degrees minus 20 degrees for angle C3 will give you that angle C4 is equals to 70 degrees. Okay, on the other side, we will have that angle C1 is equals to 80 degrees. Okay, all right, so what else? We've used the cyclic quad. The cyclic quad unfortunately does not have any exterior angles. Okay, so we can't use that. We've used the property of the cyclic quad, which is the opposite angles being supplementary. What else do we know about cyclic quads? Right, we also know that if we can prove the converse of angles in the same segment, we prove a cyclic quad. All right. In this diagram, I don't really see any angles in the same segment. Okay. And then lastly, before we actually get to the questions, I do see something else. It's hiding itself in this rider quite nicely. Okay. If you look at this arc NC, okay, you will see that what's sitting on this arc NC, right, or what this arc NC subtends, okay, is first of all an angle at the center. That's the first thing. Okay, which angle at the center? Well, angle O1. Okay, and something else that is also being subtended by this arc NC is this angle D1 at the circumference. Right, so you can see that we have that angle at the center is equal to 2 times the angle at the circumference, relationship being set up over here, and it's being hidden quite nicely in this rider. Right, quite a difficult one to identify, but I did see it eventually. Right, so I'm going to put 2 lines right at angle O1 just to remind me that angle O1 is twice angle D1. Okay, so there is quite a lot that is happening in this diagram, and we actually haven't used our parallel lines, right? So let's use our parallel lines quickly. Okay, first things first, we can obviously see that we've got some alternate angles happening over here, right? We've got that angle C2, C3, sorry, angle C3, right? That is alternate with angle O1. Oh, okay, so let's put a blue stripe over there as well. Okay, so let's just check again. Yes. Okay, So angle C3 is equals to angle O1, and that is alternate angles, right? We also have over here some corresponding angles, right? Remember that we have this 90-degree angle on this other side as well. So basically, if you extend, right, this line OE, right, we're going to extend it for ourselves. Okay, just so that you can see, but you would basically be doing this mentally, right? We can see over here that we have this whole F setup, right? We've got this being parallel to that, right? Then we know that this angle will equal that angle. Those are corresponding angles, right? So there we go. There's the 190-degree, right, which is underneath the parallel line. So then underneath this parallel line as well, we now have a 90-degree angle here for angle O1 plus O2. So let us now go to the questions and let's see what do we have to answer. Alright, question 8.1 says, calculate with reasons, right, the size of 8.1.1, okay, we're looking for the size of angle O1. Okay, so angle O1 is right over there, right? We connected angle O1 to angle D1, okay? But then we don't actually know what angle D1 is, right? They're talking about here calculating the size of this angle, okay? Angle O1 is also connected to angle C3, right? And we connected those two by the alternate angles, okay? Angle C3 does have a value. It is 20 degrees, right? So then, therefore, the value or the size of angle O1, okay, is equals to 20 degrees, okay? What is our reason here? The reason is because of alternate angles equal. And what are the parallel lines? Well, the parallel lines is OF parallel to BC. Okay. Next one, 8.1.2 says calculate the size of angle D1. Well, now we know that angle D1, if we work backwards, right, angle D1 is going to have to be half angle O1. Okay, so let's rather not state it like that. Let's state it as the theorem states. Okay, right, so the theorem says that the angle at the center is twice the angle at the circumference, right? So we should actually write here that angle O1 is twice angle D1, right? So that we can write our reason that the angle at the center, right, is equals to 2 times the angle at the circumference. And then from here we can then rearrange to get to what we were talking about. Angle D1 is then equals to half angle O1, and then this is then equals to half of 20 degrees, which is 10 degrees. Okay, so let's add that information onto the diagram. Angle D1 is now 10 degrees. Angle O1, I'll just do this. Okay, angle O1 is 20 degrees. Right, question 8.1.3, okay, is asking you to calculate the size of angle C2. Okay, so let's find where is angle C2. Well, angle C2 is that small little angle in there. We already calculated that it is equals to 10 degrees, right? But now we basically need to state the reason why did we say that. Well, the way that we found this 10 degrees is that we use the opposite angles of a cyclic quad. Okay, so we said that angle, let's call it the way they called it in the statement, right? DAB plus, right, angle DCB, right, that's equals to 180 degrees. What is this? Well, this is the opposite angles of a cyclic quad. Okay, so over here we're now just going to substitute 180 degrees, and then we're going to expand this out. We know that angle DCB is equals to angle C2 plus angle C3. All of this must equal 180 degrees. Okay, now angle C3 is actually equals to this angle, angle OCE. Okay, so angle OCE. Right. But anyway, we can just recognize that instead of writing it down. So we're going to do another substitution of 150 degrees plus angle C2 plus 20 degrees is equals to 180 degrees. Right, so then therefore, angle C2, we don't even need to show that simplification, is equals to 10 degrees. Question 8.1.4, right, we now need to calculate the size of angle D2. Okay, so angle D2 is this angle all the way up here. We connected this angle to angle C4, right? And we calculated the size of angle C4 using the relationship between the radius and the tangent. Okay, so that's where we need to start off. Okay, we first need to say that OC, right, is going to be perpendicular. Let's use this full length GF. Okay, what's our reason over here? The reason is because we have a radius, which is OC, which is perpendicular to the tangent. Okay, that's what creates that relationship over there. Okay, so then from this relationship, we have that therefore, okay, angle C3 plus angle C4 must equal 90 degrees. Okay, we know that what angle C3 is. Angle C3 was given to us as 20 degrees plus angle C4 equal to 90. Therefore, angle C4 is equals to 70 degrees. Right, and then we have that but angle C4 is equals to angle D2. And what's the reason for this? Well, it's the tan-chord theorem. Right? Tan-chord theorem. Okay, so then therefore angle D2, which is what they are asking us about, is equals to 70 degrees. Okay, so now let's see what question 8.2 has for us. We have that if it is given, right, that OF is equals to the square root of 3y and EC is equals to 2x, the area of OECF. Okay, they said something about OECF in the beginning. Okay, no, they didn't. Right, but OECF, right, OECF is this figure over here. Alright, so we can recognize for ourselves that this figure is a trapezium since it has two parallel sides. Okay, so that figure over there. Alright, so we are given the area of that. So let's just write this down quickly. So what are we given? We're given, right, that for this figure that looks like this. Okay, we've got O, F, C, and E over here. Okay, we are given that OF, right, is equals to root 3y, and that the area of this figure is equals to 3 over 4 y squared minus x squared. Okay, we are asked to determine the length of OE, right, so to determine the length of OE, which is this, right, in terms of x and y. Okay, so this is basically now just going to be solving an equation, right? So we know, okay, that the area of the trapezium, right, that is equals to, right, half the sum of the two parallel sides, so half of OF plus EC, right, that's the sum of the two parallel sides, okay, times the perpendicular height. Okay, what is going to be the perpendicular height over here? Well, if we go back to our original diagram, we know that we actually have a 90-degree angle here at angle O, right? So that perpendicular height is actually this length OE, okay? So we can substitute that in. So this is half OF, which we are given, plus EC, which we are not given, okay, times what we are looking for, OE. And we are given that this area is equals to exactly that. Okay, so I'm just going to move this over. Right, so I'd just like to correct myself very quickly. I just noticed that we are actually given the length of EC. I just didn't write it down. Okay, so EC is given as 2x. Okay. Right, so now we just need to add one more thing to this so that the solution is complete. Because if you can think about it, we didn't actually state the reason why all of a sudden we have a 90-degree angle over there at angle O. Okay, so before all of this, right, you would have this statement. Okay, so you would start here. This would be the first part of the solution, and this should be the second part of the solution. Okay, even though the thinking started here. Okay, so what is the first part of the solution? The first part is to say that angle E1, right, is equals to 90 degrees. And the reason for this is because we have a line from the center, right, perpendicular to chord. Okay, that's what created that 90-degree angle over there. Okay, so then from there we have that angle O, let's say angle O1 plus angle O2, so that we are a little bit more clear about what we're talking about, is equals to 90 degrees, and the reason here is corresponding angles. Okay, and the parallel lines is OF parallel to BC. Okay, so that would be the first part of our solution. We need this, right, written down so that we basically have some sort of statement that explains why we have that 90-degree angle over there. Okay, and then now that we have that 90-degree angle over there, the length OE becomes a perpendicular height. Okay, so which then explains why we made a substitution for h over here. Let me just add that perpendicular over there, so you can remember that this is the perpendicular height. Okay, so now it makes sense that this substitution for perpendicular height is made with OE. Okay, the question said determine the length of OE in terms of x and y. Okay, so we do definitely have x's and y's over here. We just need to simplify and solve for OE. Okay. Right, so let's carry on with our substitutions over here. We have 3 over 4 y squared minus x squared is equals to a half times the root of 3y plus 2x times OE. Okay, so times OE. Alright, so in order for us to solve for OE, therefore OE must equal 3 over 4 y squared minus x squared divided by a half of the root of 3y plus 2x. Okay, we can now distribute this half into the bracket over here, like that. So if we do that, we will have that OE is equal to 3 over 4 y squared minus x squared divided by the root of 3 over 2y plus, well, a half times 2 is going to be 1, so just plus x. Okay. Right, so it might look like we are actually done over here, right? We have an expression for the length OE and it is in terms of x and y, but it is not in its simplest form, okay? Quite difficult to identify this one, but this is actually a difference of two squares, okay? So let's factorize that out. Right, so all that we need to recognize here is that the square root of 3 times the square root of 3 is equal to 3, or you can think about this as the square root of 3 all squared is equal to 3. Right, so I'm going to carry on up here. This now allows you to write OE, right, as basically, let's write it as the square root of 3 squared, right, and we know that 4 is 2 squared, okay? We have that y squared minus x squared divided by the root of 3 over 2y plus x. Okay, so we can now factorize this top, right? Difference of two squares, we know that basically just the components, right? So if you have a squared minus b squared, right, this factorizes into a minus b times a plus b. Okay, so it's a little bit hard to see over here, but you can, maybe let's do that step, right, of writing this as the root of 3 over 2, all of that squared. Okay, then you have y squared minus x squared divided by the root of 3 over 2, y plus x. Okay, so then OE is going to equal, right, in two brackets, the first thing, right, which is squared, is the root of 3 over 2, then we have a y, then we have a minus, and then the second thing that's squared is a x. Okay, now we need the same bracket, right, just with a plus sign. Okay, so that is us factorizing that difference of two squares. I've run out of space, so that's why it looks like that, but you basically get the idea that this is two brackets, right, being multiplied with each other, and they still be divided by the root of 3 over 2y plus x. Okay, now this cancels out with this bracket, okay, which gives us a final answer, right, that OE is equal to the root of 3 over 2 times y minus x. Okay, all right, so while this step over here, okay, this one over here that I'm highlighting in green, while that step is actually correct, right, this is a valid equation for the length OE in terms of x and y. The only thing about it that they didn't really add to this question, which is something that we do know we need to do, okay, is to leave our answers in simplest form. Okay, so if you had stopped over here, you would have lost a few marks, okay, maybe 2 marks, for not recognizing the fact that this, right, is a difference of two squares. Right, first time in this paper that we've actually got to quite an interesting question. I did actually enjoy this question. So if we carry on scrolling over here, right, we notice that question 9.1 is the theorem, right, or the proof, and we've already done this. Okay, We notice the fact that this is 9.1, so which means that we still haven't done 9.2. Okay, so which is what we need to move on to now. Alright, so let's see what do we have over here. We have that in the diagram below, the center, right, of the circle is O with diameter KL. M and P is a tangent to the circle at N, right? So we're being told that this line M and P, right, is a tangent. And we have that that is the center. Okay. We also have the chords KN, right? So KN and LN are drawn. R, right, is a point on KN, okay, and ORSP forms a straight line. Okay, so basically, now that they've actually told us that this line, right, they've named all the points on the line, ORSP, okay, the fact that they've told us that this is actually a straight line, okay, and we also know that KN is a chord, right? By definition, a chord is always a straight line. It means that we are being allowed over here, right, at this point R, to start making use or to start thinking, right, of all the relationships that we know in terms of lines. So things like the adjacent angles on a straight line are supplementary, right, or vertically opposite angles are equal, right? So yeah, that now establishes that relationship over there. And we also have that OP, okay, so the length OP is equals to 15 units. Right. Question 9.2.1 says, give the length of OR, right, if OR to RP is 2:3. Okay, so we are given that OR to RP is equals to 2:3. Okay, so what are they talking about? They're talking about this distance, OR, okay, to RP, that is in the ratio 2:3. Okay, what do they want us to find? They want us to give the length of OR. Okay, so which means that we can now set up an equation over here. How about instead of just looking at these individual segments, right, we now actually look at what is the ratio of OR, okay, to the full length OP, right? We know that that's going to be 2:5, right? So then we can write that down. OR to OP is in the ratio, right, 2:5. Okay, so now we are given the actual length of OP, so then we can therefore calculate the length of OR, right? The length of OR is going to be 2/5 of OP. Okay, so then 2/5 times 15, okay, this is going to give us 2, right, over 1 times 3, so that is going to be 6, right? So 6 units is the length of OR. Okay. Question 9.2.2 says, if it is given that KR squared minus KO squared is equals to 36, prove that OR is perpendicular to this diameter KL, right? So in other words, we need to prove that we have a 90-degree angle over there, right? Now let's find these two lengths, right? KR is this length over here, and KO is this length over here. Okay, so this length here, right? So which means that if we want to prove that OR is actually perpendicular to that diameter, obviously that can happen if the theorem of Pythagoras, right, actually holds in here, right? So what we'll be doing is we're going to be using the theorem of Pythagoras, right, in reverse, right? Or in other words, we'll be using the converse of the theorem of Pythagoras, right? So let's just note what that theorem says quickly. Right, so what the converse of the theorem of Pythagoras states is that if the square, right, on the longest side of your triangle, okay, so now if we look at this triangle KOR, right, the longest side is this side KR, okay, so now if the square of that side, right, so KR squared, if that is equals to the sum of the squares of the other two sides, then we can conclude that that triangle is actually the right angle triangle. Okay, so let's now say, okay, for this solution, we're going to say, well, we've identified that we need to work in the triangle KOR, right? Then we're going to say KR squared minus KO squared is equals to 36, and this was given to us, right? So then from there we want to show this relationship here by focusing on this largest side, okay, KR, and we want to look at the square of that. Okay, so if you rearrange this, this is going to be 36 plus KO squared, right? This is an O, I know it looks like a D. Okay, now if you look over here, right, we already have the side KO, we are just missing this other side OR. Okay, in the previous question we just calculated that OR is 6 units long. Okay, now it just happens that 6 squared is actually 36, right? So we can make a substitution over here for 36 as 6 squared, right, plus KO squared, and then make a substitution for 6 for the length OR. Right? So now we've actually proven the converse of the theorem of Pythagoras. We've now shown that the square of the longest side of the triangle, right, is equals to the sum of the squares of the other two sides. Okay, so then we can now then conclude that therefore triangle KOR is right angled, and we can say with angle O1 being equal to 90 degrees, so then therefore OR is perpendicular to the diameter. Right, moving on to question 9.2.3. Okay, it says prove that ORNL is a cyclic quadrilateral. Right, so let's first identify where this is. ORNL, okay, is this figure over here. Okay, so we have to prove that that is a cyclic quadrilateral. Right, so let's go back to the main diagram on this side and let's put in some angle relationships. Right, we haven't actually studied this diagram in quite some detail. Okay, so one of the angle relationships that is quite apparent over here is that we have an angle in a semicircle. Right, KL is the diameter, so then angle N2 is equals to 90 degrees, right? That's an angle in a semicircle. What did we just prove? We proved that OR, right, is perpendicular to the diameter, so we also have a 90-degree angle over here at O1 and at O2. Okay. Okay, so what else do we have? Let's use the tangent. Okay, so if we look for the tan for theorem, we can see that angle N1, right, is going to be equals to, and we use another color here, right, so angle N1, that's going to be equals to angle K up here. Okay, we also have that on the other side, right, angle N3, this side, angle N3, by the tan theorem as well, that's going to be equals to angle L. Right, so hopefully right now you can see that we actually have two similar triangles, right? So which two triangles am I talking about? I'll draw them in the right orientation, the way they're drawn over here. I'm talking about the triangle KOR, okay? So KOR, right? And I'll tell you now why I'm saying they're similar. Well, because I have two angles in these two triangles. I'll tell you what the second triangle is now. Hopefully you can see it yourself as well. Okay, but basically I've identified two equal angles in two different triangles. Okay, this is the first one. I've identified that I have a 90-degree angle there at O1, and I also have angle K, right, being common in both of these triangles, right? So that's the first one. The second one is this larger triangle. Okay, so why was it necessary for me to actually observe this? Well, because now you can see that we've actually proven our cyclic quad. Okay, so you have that from the similarity, okay, so because these two triangles are similar, you now have that angle, right, R1 is equals to angle L, right? But angle R1 over here, right, angle R1 over there is equals to angle R3, and those are vertically opposite angles, okay? So because angle R1 is equals to L, it means that angle R3 is also equals to L. So then we prove that this is a cyclic quad, right, based on the fact that the exterior angle is equals to the interior opposite angle. If you are struggling to see this right in this complicated diagram, if we go back over here, the simplified one here, right, what we've just proven is that this exterior angle, right, is equals to the interior opposite. Okay, and now because this is for like a four-sided figure, right, we then say that that four-sided figure is a cyclic quadrilateral, right. Question 9.2.4, okay, is a long story about moving this tangent, right? Remember that we were told that MNP, right, is a tangent. Okay, it's a long story that talks about moving this tangent to the left-hand side of the circle, right, such that the new point M falls outside of the circle, the new point M inside of the circle, and the new point P, right, coincides with the point S. Okay, so in other words, what they're trying to say over here is that we are going to move this tangent such that P is now going to be in the exact position where S is, okay, and then angle M, listen to me saying angle M, the point M, right, still has to be outside of the circle, right, so something like that, okay, and then they go on to say that the points O, L, and S, right, remain fixed as indicated on the original diagram, and now the original tangent is parallel to this new tangent, right, which is going to be, we know that here at S we actually have P prime, right, and then we are going to have the point, maybe let's try to somewhere there, okay, N prime, and then we're going to have M prime over here, right. So that's the new tangent, or the new position of the tangent, okay, and it is now parallel to this old tangent over there, okay. The question is it possible for this new position, right, to be a tangent to the circle drawn through O, L, and S, right, and then we need to motivate your answer. Right, so the way that I would set this out is that I would first start off by taking a position, right? So because I know that one of the marks is going to be to say whether or not this is a tangent, okay, because that's the question, right? So you need to take a position, right? So I would take a position and say that, well, m prime n prime p prime is not a tangent. Okay, so now I know that I at least have one of my marks. Okay, it said motivate your answer, right? And here's the part where I'm actually motivating my statement. Okay, because since this new position, right, m prime n prime p prime is actually parallel, okay, to the old tangent m n p, right? And also another thing that is happening over here is that the point P prime, right, coincides, right, with the point S. Okay, so over there we actually have for the point S, if we write this properly, okay, right, what we actually have is that on top of this point S, right, at exactly the same position, right, you actually have P prime. Right, so that's what we mean when we say that P prime, right, coincides with point S, right? So it lies exactly on the same position, okay? So then if that is the case, what happens is that this new position m prime n prime p prime, okay, effectively intersects, right, the circle, and then if it intersects the circle, it no longer becomes a tangent. Okay, so yeah, that would be my reasoning. If you can find any other way that you want to answer this question, you are more than welcome to use that approach as well. Alright, so now let's move on to our last and final question, right, question number 10, which is then going to allow us to then conclude this question paper. Right. So we have that two circles touch each other internally at the point B. O is the center of the bigger circle, right, and it lies in the circumference of the smaller circle. We've got a tangent FBG, right, so let's just note that down before we carry on. FBG is a tangent. Alright, we also have that AB and BC are chords of the bigger circle, and these two chords intersect the smaller circle at D and E respectively. Okay, AHG, right, forms a straight line. Okay, so AHG, that is a straight line. Okay, that is actually very necessary for them to tell us that AHG is a straight line, because if you can see, AHG is actually having connected to it, right, these two parallel lines. Okay, now whenever we want to use the properties of parallel lines, which is alternate angles, corresponding angles, or co-interior angles, right, all the lines that are involved have to be straight lines. Okay, obviously the parallel lines are automatically straight, right, and then we just need to make sure that the other line, which we call the transversal, right, which cuts through these parallel lines, is also straight. Okay, they could have also just maybe if this was in a circle completely, they could have just spoken about the chord, right? A chord is also by definition a straight line. Okay, we also have that the chords OD, who is that? Okay, OD, DE, and OB, right, of the smaller circle are drawn. Okay, right, so look at this over here, right? They're using a very interesting way to tell us that AG is twice AH. Okay, so what they're saying is that you were given, right, that AH to AG is in the ratio 1:2. Okay, let's write this out as a fraction. AH to AG, okay, which is basically this, right? AH to AG, right? We are saying that that is in the ratio of 1:2. Okay, now if you cross multiply over here, you're going to have that AG, okay, is equals to twice AH. Okay, so what do we know now? We now know that basically if the full length, right, AG is equals to twice just one of these lengths AH, it means that AH is equals to HG, right, which makes H the midpoint of that line segment AG. Okay, now if you see over here, we also have a triangle ABG, right? Right, so if you look at the triangle AGB, right, which I've now highlighted in purple, okay, we can see that what we have in this triangle is that we have our theorem, a line drawn parallel to one side of the triangle, okay. We know that that theorem says that that line, okay, basically divides the other two sides in the same proportion, okay. So which means that we can therefore say that AD to DB is going to be equals to the same ratio of AH to HG, okay, and this is in a ratio of 1, okay, so 1 is to 1, okay, so this basically just states that AD is equals to DB, okay, so AD is equals to DB, okay, making D the midpoint of the line segment AB. Okay. Right, let's see what else can we pull out of this diagram. Well, let's carry on over here in this triangle since we are now still within it. Okay, so one thing now that I can see is our corresponding angles. Okay, so we now have that angle G, right, is corresponding to angle H over here. Right, more accurately, angle AHD is corresponding to angle AGB. Okay, and also on the other side, right, we have B1, okay, being corresponding to this angle over here, but then there's no label there, so, and there D, you have quite a lot of angles happening there, so I don't want to cluster it. If we need it, we'll use it. Okay, right, another thing that you can see is that we have a tangent, right, which is connecting with the radius of this larger circle. Okay, remember that they said that O is the center of the bigger circle, so which means that OB is the radius of the larger circle. Okay, so angle B1 and angle B2 will equal 90 degrees. Okay, tangent perpendicular to radius. Right, in the same breath, right, because remember we have two circles here that are sharing this tangent, right? This tangent is a common tangent, okay? So we have to think both in the bigger circle and in the smaller circle sort of like at the same time, okay? So in the same breath, we can use the converse of this theorem now that we have that 90-degree angle over there, right? What we can now say is that, well, because this line, right, because in the smaller circle, OB is just a line, okay, we are in the smaller circle right now, that line forms a 90-degree angle with a tangent, okay, so then the converse of that basically then tells us that that line is the diameter of that circle, okay, so we now have that OB, right, is the diameter of the smaller circle, right, of the smaller circle, right. The reason of this is the converse, right, of let's say radius We don't actually have to say radius, because if you carry on drawing that, it is still perfectly acceptable to talk about a diameter. Okay, so converse of diameter perpendicular to tangent. Okay, so if then OB is now the diameter of the smaller circle, it means that now what we have is an angle in a semicircle there at D. Right, so all these angles D2, D3, and D4, all of those are equals to 90 degrees. Okay. Okay, so what else? Well, going back to that purple triangle, okay, notice that what we've done, okay, in the beginning is that we've proved that H is the midpoint of the line segment AG and D is the midpoint of the line segment AB. Okay, so basically what we have right now is the midpoint theorem. Okay, because we now have this line segment HD, right, which is joining the midpoints of two sides of a triangle. Okay, we know that the midpoint theorem states that that line is parallel to the third side of the triangle, and also that line, okay, HD, is going to be half the length of that third side, right? So it's going to be half the length GB. Okay, so this over here is the midpoint theorem. Okay. Are we done? Certainly not. We haven't used our tangent yet. Okay, so let's see what relationships does the tangent establish in this diagram. Okay, so let's start here with this angle B1. Okay, hopefully you can still see in this clustered diagram. Okay, so if we look at the angle B1, right, maybe let me use a different color. Right, angle B1. Okay, so angle B1 is touching two chords, right? It's first touching the chord of the larger circle, which is the chord AB. Okay, so if it's touching that chord in the larger circle AB, what is the chord AB subtending at the circumference? Well, unfortunately, it's not subtending anything. Okay, so we can't use the tan chord theorem in terms of the larger circle, okay, but we can use it in terms of the smaller circle, right? It also connects to the chord DB in the smaller circle, and that chord DB in the smaller circle is subtending the angle E2 at the circumference, right? So by the tan chord theorem, those two are equal, right? What else do we have? We have also on the other side, right, if we look at angle B4, right, angle B4 is connecting with this chord, right, BC, and that is the chord of the larger circle, right. So what is BC subtending at the circumference? Well, if we go to the larger circle, it's not actually subtending anything for the larger circle, okay, but is it subtending something for the smaller circle? Yes, it is indeed. If you look at this chord BE, right, that angle, that chord BE is subtending the angle D4 right at the circumference. So angle D4 is equal to angle B4 right by the tan chord theorem. Okay. Let's see if we can use these parallel lines any further. We've already used corresponding angles. Maybe we can find something else. Let's try to look for alternate angles. Okay, so there is the parallel lines, right? One of the transversals that we can see is, okay, and the transversal is just a line, right, that is connecting the two parallel lines. Okay, so one of the transversals that we can use over here that is quite useful is this transversal BC. Okay, that is connecting these two parallel lines. Right. Over here we can most definitely use alternate angles, right? if you go this way and then come back down, go back up, you have that angle B4, right, now also connects to this angle down here, angle C, by alternate angles. Okay, there is other alternate angles over here. If you look at the transversal AB, right, you can see that B1, okay, is alternate with the angles, right, D3 plus D4. Okay, there's quite a lot happening over there, so maybe we might not use it. If we need it, we'll go back to it. Okay, we don't want to put too much information on the diagram. Right, so that was one transversal. Another one is OB. Okay, OB will tell you that angle B1 plus B2, right, will be alternate to this angle over here, so which means that there's a 90-degree angle there. Nothing is labeled there, so we actually won't even need to use that. Okay, so yeah, I think so far we should be ready now to actually go to the questions. Okay, question 10.1. Right, this one just says give a reason why the following angles are equal. Okay, 10.1.1, we want to know why is angle B4 equals to angle HCB. Right, so angle HCB, right, is this angle over here. Okay, that angle there, this one, that is angle HCB. Right, so this angle, we just connected it now with the angle B4, right, through alternate angles, right? So the reason here is that we're going to say alternate angles equal, right, with HC parallel to GF. Okay, question 10.1.2, we want to know why is angle B4 also equal to angle D4, and we already identified that for ourselves. That was through the tan-chord theorem. Right, tan-chord theorem. Next, question 10.2, right, 10.2.1, we have to prove that triangle DBE is similar to triangle DBC. Okay, let's find those two triangles. So triangle DBE is a small triangle over here. Okay, let's draw it out. Triangle DBE. Okay, so let's see. There's E over here, and with E we're specifically looking at E2. Okay, we've got angle B over here, and that is specifically angle B2 and angle B3, but we'll just leave it like that for now. And then we have up here for angle D, we have the angle D4. Okay, so that is the first triangle, triangle DBE, right? Other triangle, triangle DBC, looks like this. DBC. Okay, we've got C over there, we've got D over here, right? And if you look, we're looking at angle D3 plus angle D4, okay? And also for B, again, we're looking at angle B2 and B3. Okay, so we've already found two angles, right, in two different triangles which are equal to each other. Okay, the first one is angle B2 plus angle B3 is common to both of these triangles, right? The second one is exactly what we just proved right above. Okay, we proved that angle HCB is equal to angle D4, right, since both of them are equal to angle B4. Okay, So if we take this to these individual triangles, we basically just prove that angle D4, right, is equals to angle C. Okay, right. So the condition of similarity has been met. In two different triangles, we have two equal angles. Okay, so we just need to write this down. Right, so notice something over here, right? Usually, the way that they give these similar triangles is as per equal angles, right? But in this question paper, they didn't do that, right? If you see over here, what this is trying to say is that angle D is equals to angle D, but we know that angle D in these two triangles are not actually equals to each other, right? So which means that the order over here is not correct, okay? So we need to conclude the similarity in the correct order, right? So we then have to say, therefore, triangle, right? And you just state it using the equal angles, right? If you want to state it the way they did, you want to start with angle D, B, and then E, right? You would then have to now think properly because it's not exactly the way it was given to you. Angle D, right, if you think about it, is if you look at the smaller triangle, right, DBE, right, angle D4, we said that is equals to angle C. Okay, so over here you would have C. For angle B, well, angle B is equals to angle B in both triangles, so that would be B. Okay, and then lastly, angle E in the small triangle, which is E2, that would be equals to angle D3 plus D4, right, in this larger triangle, right? So the next letter over here has to be D. Okay. Okay, so we're going to note that result up here. DBE is similar to triangle CBD. Okay, it's important for that order to be correct because you remember that we use similarity sometimes to get our proportional sides. Okay, so it's very important for that order to be as per equal angles. Okay, we also just need to conclude over here. Why are we saying that these are similar? Well, we're using angle-angle similarity. Angle-angle similarity just means that we've found in two different triangles, right, two angles which are equal, and thus the third angle is equal to each other. So then basically these two triangles become equiangular, and equiangular triangles are always similar. 10.2.2 says prove that D is the midpoint of AB. Oh, okay, we've already done that. Okay, so to prove that D is the midpoint of AB, we did that up over here, right in the beginning. So this is 10.2.2. Okay, if I can just remind you what we said, we basically started off with the given information, right? Remember that we were given that AH, right, to AG was in the ratio 1:2. Okay, so then we wrote that as a fraction, and that helped us to see that in fact this is quite a clever way to just tell you that the full length AG, right, is twice one of these lengths AH. Okay, so then if that's the case, it means that AH has to be equals to HG. Okay, so that immediately made H the midpoint of the line segment AG. Okay, so then after that we then applied, right, the theorem. Okay, I didn't write it over here. The reason for this step was a line, right, drawn parallel to one side of a triangle, right? So we applied that theorem and we wrote down the ratio of AD, right, to DB, and we saw that it has to be in the same ratio as AH to HG, right? And since AH and HG were equals to each other, that was a ratio of 1:1. That then made the line segment AD equal to the line segment DB. Okay, so then we can conclude here that therefore D is the midpoint of AB. Okay, so that was question 10.2.2 that we did right in the beginning through analyzing the diagram. Okay. Right, so now on to question 10.2.3. Okay, it says prove that AB squared over 4 is equals to BC times BE. Okay, so let's use this diagram to identify these things. Okay, so where is BC? BC is this length over here. It does want to go away. Okay, but basically that is BC. Okay, where is BE? Okay, BE is that side over there. Okay, so now notice that those two sides, okay, come from this similarity that we worked with before. Okay, BE is the smaller side and then BC is on the larger triangle. Okay, so which means that we are most definitely going to have to use the similarity in order to get those proportions. Okay, what else do we need? We need AB, right? AB is the full length, right, which is made up of one of these sides in these similar triangles, the side DB. Okay, so which means that if we want to eventually get to this AB squared, we can do that. Okay, we just need to write down a ratio that connects DB and BE and BC. Okay, so let's do that. Right, from the similarity, we're looking for DB. Okay, so that's the first 2 DB, and that's going to be over the first 2 right in the second triangle, which is going to be CB. And then over here, you can see that the next 2 is BE, which is something that we are looking for. BE. Okay, so if you take the next 2 in the other triangle, that gives you BD or DB, right? BD and BD is the same thing. Okay, so then from here, if we cross multiply, right, we just need to write a reason here. The reason is this is triangle DBE similar to triangle CBD. Okay, that's where we got this proportionality. Okay, so then therefore from here, if we cross multiply, we'll get DB squared. Okay, that's going to equal BE times CB. Okay, now notice that CB and BC is exactly the same thing. Okay, we just swapped the lettering around. Okay, now we have to eventually get to AB, right? And we know that AB is connected with DB. Okay, basically we can write that AB is twice DB. Okay, remember that we proved that D is the midpoint of the line segment AB. Okay, so then from there, if we want to make a substitution for DB, we would have to divide both sides by 2, which will give us AB over 2. Okay, so this is sort of like equation 1, equation 2. We're now going to sub equation 2 into equation 1. And that will give us AB over 2. And that has to be squared. And this is equals to, let's write it the way they wrote it. Okay, let's start with the BC times BE. Okay, final step, just applying the square will give us AB squared divided by 2 squared is 4, so that gives us that part. Okay, and this is equals to BC times BE. There we go. Right. The next question says we need to prove that CE, right, CE to BC, like that, okay, is in a ratio of 5:9. Okay, and we need to do that if we are given, okay, so 10.2.4, okay, we need to do that by using the information that DB is equals to 3 units and BE is equals to 2 units. Okay, so these links look very familiar. BE, we just saw a BE over there. Okay, we also saw a BC over here. Okay, so this is sort of like connecting to what we have from before. And we also saw DB, okay, as being twice AB. Okay, so if we look at what we just proved above, okay, so we can say from above, AB squared over 4 is equals to BC times BE, okay, and AB is equals to twice DB. Right, so if we substitute this result into there, right, we are going to have 4 squared times DB squared, right, so then therefore DB squared, since the 4's will cancel out, is equals to BC times BE. Okay, so then DB is given to us as 3, right, so that's 3 squared is equals to BC times 2. So this will give us 9 is equals to BC times 2. So then therefore BC is equals to 9 over 2 units. Right, so looking at this ratio, right, we now have the length BC. We just need to find out what is the length CE. Okay, so now going back to the diagram, if you go back here, right, notice that CE is a portion of the length BC. Okay, so we can write the equation BC is equals to BE plus EC. Okay, don't let this confuse you. EC is exactly the same length as CE. Okay, it's just a different order. Okay, so if we substitute in here again, 9 over 2 is equals to BE, we already know is 2, plus EC, then EC will work out to be 5 over 2 units. Okay. Right, so then if we take these two results and then we conclude by actually finding the ratio now, we're going to say therefore the ratio CE, okay, to BC is going to be these two lengths divided by each other. Okay, so it's going to be 5 over 2 divided by 9 over 2 or multiplied by 2 over 9, okay, which is going to give you the ratio 5:9. Okay, so CE to BC is in the ratio 5:9. Okay. Okay, now for the last question, question 10.3. Okay, it wants us to calculate the ratio of the area of triangle AHD divided by, this is a D, okay, the area of triangle HGB. Okay, so if we identify these two triangles, okay, I'm going to do it in a blue color. AHD is this triangle over here, right? AHD. And then HGB is going to be this triangle over here. Right, so those two different triangles. Notice that these two triangles are not right angled triangles, so in order to calculate their areas, we're going to have to lean towards the sine rule. Okay, so let's go for the sine rule. We're going to have half, right? 2 of the including sides, and the including sides is going to be the side AH times HD times the sine of the included angle, which in this case is the angle AHD. Okay, that angle right over there. For the other triangle, we'll do the same thing. We're going to have 1/2, right? So the including side is going to be HG times GB times the sine of angle AGB. Okay, so now there's a few things here that we can cancel out. Obviously, the 1/2 will cancel out. The AH and the HG will cancel out since those two lengths are equal. And the sine of angle AHD and the sine of angle AGB will also cancel out since those two angles are also equal. Okay, so we just need to write that down over here. We'll write here since, okay, angle AHD is equal to angle AGB, right? And these are corresponding angles. HC is parallel to GA. Okay, so we've now simplified this as the area of triangle AHD to the area of triangle HGB to being the ratio of HD divided by GB. Okay, but now remember what we said up here when we looked at the midpoint theorem. Okay, we said that this line, right, which connects the midpoints of two sides of a triangle, we said that that line is parallel to the third side of the triangle, but it is also equals to half the length of that third side. Okay, so we established that relationship between HD and GB, right, using the midpoint theorem. So we're going to substitute it in over here. For HD, we're going to substitute 1/2 GB, and that's still divided by the side GB. Okay, now again, the GBs will cancel each other out, leaving us with a ratio of 1/2. Okay, so that will then be the area or the ratio, okay, of the areas of these two triangles. Alright, so then with that said, matriculants, well done. We have now reached the end of this question paper. Okay, it was a long one, but hopefully by looking at the questions in this question paper, you at least were able to revise some of the key concepts that we look at in paper 2. This one was actually quite a difficult one, so you should be able to then identify where are your weak points and where you should start grabbing more past papers and get yourself practicing. Okay, I wish all of you all the best in this possible rewrite, and I hope that everything goes well. Okay, until next time, guys. Bye.